Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, science speaks softly, and the universe is invited to explain itself at a slower pace. Tonight, we begin a gentle journey through one of humanity's oldest hopes and newest questions. Are there any other planets we can breathe on? It is a surprisingly personal question, isn't it? We can dress it in the language of astronomy, chemistry, engineering, and telescopes, but beneath all of that sits something very human. We're asking whether somewhere beyond the night sky there is another place where lungs could fill easily, where skin would not blister in the air, where a breeze might pass over fields we have never seen, and where a person could simply stand outside and take a calm breath without a machine. For creatures who spend so much of life barely noticing the atmosphere around us, we become very emotional the moment we imagine losing it. Perhaps that is because breathing is so ordinary that it feels invisible. You do it while reading this. You do it while worrying, laughing, sleeping, walking, waiting, forgetting, remembering. Breath is the quiet background task of being alive. We rarely celebrate it unless it becomes difficult. Yet the moment we picture another world, breathing becomes the first question. Not gold, not scenery, not real estate prices, not whether the neighbours are friendly. We ask about air, and maybe that is wise, because space, for all its beauty, is not built with us in mind. It offers magnificent views and very poor hospitality. There are worlds where rain may fall sideways in acid clouds, worlds where winds race faster than sound, worlds where the ground may be ice harder than stone, worlds where noon is dimmer than our twilight, and worlds so hot that metal itself would complain. Somewhere out there may be planets wrapped in thick haze, oceans with no shorelines, deserts with skies the wrong colour, and frozen spheres turning silently under stars that never rise the way ours does. Still, we keep asking, where are you listening from tonight? What time is it in your little corner of Earth right now? Is it late evening with the lights low and the day nearly finished? Is it early morning with pale light finding the window? Is it raining where you are? Warm, cold, quiet, busy. Somewhere on this planet, countless people are breathing air shaped by forests, oceans, plankton, bacteria, mountains, and billions of years of accidents that happen to go our way. That is worth pausing over. If you find this soothing, interesting, or simply a pleasant place to rest your thoughts for a while, I'd be ever so grateful if you liked the video and perhaps subscribed. It helps this calm little corner reach others who may need a softer landing at the end of the day. Now settle in. Let your shoulders drop a little. Let the mind loosen its grip on schedules and lists and unfinished things. We're going to talk about distant planets, but there is no rush. The stars have been waiting quite patiently. When many people imagine another habitable world, they picture something rather convenient. Blue skies, green valleys, mild temperatures, maybe a lake with agreeable reflections and absolutely no mosquitoes. In other words, they picture Earth with different branding. It is understandable. We tend to imagine the unknown by rearranging the familiar. But the universe is under no obligation to be familiar. If another breathable planet exists, it may not resemble home in any obvious way. Its grass, if it had grass at all, might not be green. Its clouds might glow copper at sunset beneath a red star. Its days might last weeks. Its gravity might make every staircase a negotiation. Its oceans could be deeper than anything we know, or absent entirely. Even a world that lets us breathe might still feel strange enough to remind us every hour that we are visitors. Then again, perhaps feeling strange is how all new homes begin. Think of the first humans who crossed mountain passes, coastlines, deserts, frozen land bridges, or wide rivers into places no one in their memory had lived before. They too must have wondered whether the land would feed them, shelter them, tolerate them, whether the winds were dangerous, whether water was nearby, whether winter would be survivable, whether this new horizon could become ordinary. Now our horizon has expanded somewhat. Instead of the next valley, we consider the next world. That shift happened quickly by historical standards. For most of human existence, the planets were wandering lights, beautiful, mysterious, unreachable. Then came telescopes, mathematics, rockets, probes, orbiters, landers, rovers, spectroscopy, radio dishes, giant mirrors on mountaintops, and instruments so sensitive they can detect a planet we cannot see by noticing the slight wobble of the star it circles. We went from naming bright dots to measuring alien atmospheres. Not bad for a species that still misplaces its keys. Yet the closer science looks, the more complicated the question becomes. Can we breathe there? Sounds simple, but it hides many smaller questions inside it. What gases fill the air? How thick is that air? How hot is the ground? How strong is the gravity? How much radiation reaches the surface? Does liquid water exist? Does weather arrive gently, or like punishment? Does the planet even have a surface at all? Or is it one vast crushing envelope of gas descending into conditions best described as impolite? Even oxygen, the gas many people assume is the whole story, is not enough by itself. Too little oxygen is a problem. Too much can also be dangerous. Pressure matters, temperature matters, carbon dioxide matters, trace chemicals matter, dust matters, microbes would matter, if present. The chemistry of a safe breath is more delicate than it seems. Earth makes it look easy because Earth is showing off. Our world has had billions of years to tune itself through geology, oceans, life, and feedback loops. Volcanoes release gases, rain locks some away, plants reshape the atmosphere, microbes alter soil and sea, ice reflects sunlight, clouds trap warmth, continents drift, mountains rise, life changes the air, then adapts to the air it changed. It is less like a static planet and more like a long-running negotiation. We were born into the latest agreement. That can make us forget how unusual it may be. If you had grown up on a world with orange skies and methane drizzle, perhaps blue daylight and oxygen would seem bizarre. If your home had twice Earth's gravity, our graceful little jumps would look suspiciously floaty. If your species breathed another gas entirely, our atmosphere might seem as welcoming as a cupboard full of bleach. Normal is often just local custom. Even so, we know enough chemistry and biology to say that humans are picky. Our bodies prefer narrow ranges. We like liquid water, moderate temperatures, manageable gravity, protection from radiation, an atmosphere with the right ingredients in the right amounts at the right pressure. We are not impossible to please, but we are more selective than our adventurous slogans suggest. This is why sending a person to another world is so much harder than sending a robot. Robots never complain about stale cabin air. Robots do not need coffee. Robots can remain cheerfully functional in temperatures that would end several meetings immediately. A rover can trundle across a toxic desert with admirable professionalism. A human arrives needing oxygen, water, warmth, food, shielding, emotional support, and somewhere to put the socks. Still, humans have one trait machines struggle to match. We care. We care what another sky looks like. We care how dust sounds under boots. We care whether the sunset is blue or violet or absent. We care what it feels like to stand somewhere impossible and say quietly, "I am here." That caring is powerful. It builds telescopes. It funds missions. It motivates students. It keeps scientists awake over datasets and engineers awake over bolts that absolutely must work the first time. And so the search continues. Some of the most exciting targets are planets around other stars, what astronomers call exoplanets. A generation ago we knew of none for certain. Now we know of thousands. Some are giant scorched worlds hugging their stars. Some are bloated gas planets with densities that seem to need explaining. Some orbit multiple stars. Some may be rocky and temperate. Some sit in regions where liquid water could exist, depending on many details that remain frustratingly detail-shaped. There are also nearby candidates closer to home, though nearby in space remains an optimistic word. Mars, for example, once had rivers and lakes. Venus may once have been more Earth-like before becoming a cautionary tale with clouds. Icy moons hide oceans beneath frozen crusts. None currently offer simple outdoor breathing opportunities, but each teaches us something about how planets become what they are, and perhaps how they change. Because that is another part of our question. We are not only asking whether breathable worlds exist naturally, we are also asking whether worlds can become breathable. Could we alter an atmosphere slowly over centuries? Could microbes prepare the way? Could sealed habitats grow into cities? Could domes become valleys, valleys become ecosystems, ecosystems become something almost casual? That road, if possible at all, would be long. Long roads do not necessarily discourage humans. We plant trees whose shade we may never sit under. We build cathedrals completed after lifetimes. We launch spacecraft that arrive decades later. We write letters to futures we will not personally meet. There is something deeply human about beginning work whose ending belongs to someone else. Perhaps one day, somewhere, people will breathe outdoors because others started planning long before they were born. Yet before racing too far ahead, it helps to return to a quieter truth. At this moment, the only world known to welcome unprotected human breathing is the one already beneath you. Earth does this so effortlessly that it can seem unremarkable. But consider what a luxury it is to step outside without calculating atmospheric pressure, to open a window without checking toxicity charts, to walk under clouds that are mostly water rather than acid, to complain about weather that, while occasionally dramatic, does not usually melt metal. We live inside a miracle so familiar it became background scenery. Sometimes astronomy's greatest gift is not escape, but perspective. Looking outward can make home visible again. That does not mean we should stop dreaming of other worlds. Quite the opposite. Curiosity and gratitude are excellent companions. One asks what else exists. The other notices what already does. Over the course of this journey, we'll explore what breathable really means, why Earth's atmosphere is such a rare balancing act, which planets tempt scientists most, what stars do to the air of their worlds, whether Mars or Venus could ever be changed, how alien skies might smell, look, or behave, and whether finding a breathable planet would solve as much as we imagine. Because a world can offer air and still ask difficult questions. Could we live there emotionally, culturally, biologically? Would we belong or merely persist? Would we protect it, repeat ourselves on it, or learn from arriving second? Those are questions for later nights. For now, simply imagine standing on a hillside under an unfamiliar sky. Your lungs draw in a steady breath. No helmet, no hose, no warning lights. Somewhere overhead, a different sun moves through clouds shaped by weather no human named yet. Then imagine the next breath, and the next. Most of us move through the day with a remarkable kind of forgetfulness. We forget our keys, forget why we entered the kitchen, forget the name of the actor who was definitely in that other thing. Yet there is another forgetting far more constant and far more profound. We forget the air, not because it is unimportant, of course. Quite the opposite. We forget it because it is usually there, doing its job with such quiet reliability that it fades into the background of consciousness. We notice the weather, the smell of rain, the sting of smoke, the chill of winter wind, the heaviness of humid summer afternoons. But the atmosphere itself, the invisible ocean we live at the bottom of, often escapes attention entirely, until we ask a question like this one. What does breathable really mean? At first glance, the answer seems almost childish in its simplicity. Breathable air is air you can breathe. Problem solved. Put the kettle on. But as with many things in science, the closer you look, the more layers appear. Breathing is not just about having air present. It is about chemistry, pressure, temperature, biology, timing, and balance. It is about the exact relationship between your lungs and the gases surrounding them. It is about the difference between merely inhaling and actually staying alive afterward. Humans are surprisingly demanding customers. Imagine arriving on a distant planet. You step out into a wide valley under a pale sky. There is wind in the grass, perhaps mountains in the distance, clouds drifting lazily overhead. It looks promising. You remove your helmet with dramatic confidence, take one deep cinematic breath, and immediately discover that the universe does not reward overconfidence. Perhaps there is no oxygen. Perhaps there is too much carbon dioxide. Perhaps the pressure is so low that moisture in your lungs begins to behave in deeply unhelpful ways. Perhaps the air is thick with compounds your body interprets as poison. Perhaps everything seems fine for 10 minutes, right up until it isn't. Breathable, then, is not a visual quality. A beautiful sky tells you almost nothing. Plenty of dangerous atmospheres could look lovely from a distance. Some of the most hostile places in our own solar system are visually spectacular. Venus glows brightly in our sky, serene and elegant while hiding conditions that could ruin a picnic almost instantly. Titan, moon of Saturn, wears golden haze like a romantic filter, while offering an atmosphere that would make human lungs file a formal complaint. To understand breathable air, we should begin with Earth, because Earth has spoiled us. The air around you right now is made mostly of nitrogen, about 78%. Oxygen makes up roughly 21%. The remaining small fraction includes argon, carbon dioxide, water vapour, and trace gases with jobs ranging from useful to suspiciously niche. Many people assume oxygen is the main event and everything else is filler. That is understandable but incomplete. Oxygen is vital because your cells use it to help release energy from food. Without enough oxygen, tissues begin to fail, brains become confused, muscles weaken, important systems start behaving like office printers under pressure. Yet pure oxygen would not be ideal either. In hospitals, supplemental oxygen is valuable medicine. In everyday life, breathing very high concentrations for long periods can damage tissues and increase fire risk. Oxygen is reactive. It is useful precisely because it participates energetically in chemistry. That same enthusiasm can become a problem in excess. So why all the nitrogen? Nitrogen acts as a largely stable background gas. It dilutes oxygen to safer levels and contributes to atmospheric pressure without constantly trying to set things on fire. It is the calm co-worker in a department full of excitable personalities. Pressure matters more than many people realise. If you took Earth's current atmosphere and somehow spread it too thinly, the oxygen percentage could remain 21% while still being difficult or impossible to breathe effectively. Your lungs do not merely care about percentages, they care about partial pressure, meaning how much of each gas is actually pushing into the system. That is why high mountains can be challenging. The composition of air at altitude is similar to sea level, but the total pressure is lower. Each breath contains fewer oxygen molecules available for transfer into the blood. Climbers can become dizzy, weak, nauseated, or dangerously ill. The mountain has not removed oxygen, it has simply spaced it out. Rather rude, really. Now imagine another planet with Earth-like oxygen percentage, but much lower total atmospheric pressure. On paper, it sounds promising. In practice, your body might strongly disagree. The reverse can also be true. A denser atmosphere with lower oxygen percentage might still provide enough usable oxygen, depending on the numbers involved. This is why breathable requires calculations, not adjectives. Then there is carbon dioxide, a gas people often discuss in terms of climate, but it matters directly to breathing too. We exhale carbon dioxide because it is a waste product of metabolism. If it builds up in the surrounding air, the body struggles to clear it efficiently. Headaches, confusion, panic, impaired thinking, and worse can follow. Even modest increases in enclosed spaces can affect comfort and cognition. So when evaluating alien air, it is not enough to ask whether oxygen exists. We must ask what else is there and how much. Some gases are toxic in tiny amounts. Hydrogen sulfide smells famously unpleasant and can interfere with cellular respiration. Carbon monoxide binds to hemoglobin with dangerous efficiency, blocking oxygen transport. Chlorine damages tissues, ammonia irritates and harms. Sulfur dioxide can trigger severe respiratory distress. Methane itself is not highly toxic at low levels, but an atmosphere rich in methane usually indicates a world whose overall chemistry is not designed around your weekend breathing plans. Even harmless-seeming dust can be a threat. Fine particles inhaled deep into lungs can cause inflammation and long-term disease. Imagine a planet with tolerable gas composition, but constant airborne mineral dust sharp enough to irritate every breath. The brochures would be misleading. Temperature also joins the discussion. Air that is chemically safe but extremely hot can injure airways and strain the body. Air that is brutally cold can damage tissues and complicate gas exchange. Humidity matters as well. Very dry air dehydrates surfaces. Extremely humid air can make heat regulation difficult. Breathable, then, is a package deal. We sometimes forget that lungs are not bags but living organs with delicate surfaces. Inside them are millions of alveoli, tiny sacs where oxygen moves into blood and carbon dioxide moves out. These structures rely on thin, moist membranes and precise gradients. They are efficient, elegant, and annoyingly vulnerable to nonsense. Your body also regulates breathing using carbon dioxide more than oxygen. Many assume the urge to breathe comes from low oxygen, but rising carbon dioxide is a major trigger. This is one reason strange atmospheres can be dangerous in deceptive ways. You may not always feel immediate alarm before trouble arrives. That is unsettling. So let us lighten the mood briefly by appreciating that evolution built as a remarkable system and then made it somewhat dramatic. Now consider time. Could humans adapt biologically to a different atmosphere over generations? Possibly within limits. Populations on Earth already show adaptations to altitude. Communities in the Andes, Himalayas, and Ethiopian highlands exhibit different physiological responses to thinner air, shaped by ancestry and environment. Bodies can adjust somewhat. Red blood cell production can rise. Breathing patterns change. Circulation adapts. But there are limits between different and alien. No human population is going to evolve to enjoy breathing chlorine because housing prices were attractive. This distinction matters when people discuss colonizing other worlds. If a planet's atmosphere is close to Earth's, perhaps habitats could gradually reduce technological dependence. If it is wildly different, sealed environments may remain essential indefinitely. Terraforming, the idea of reshaping a planet's atmosphere to suit us, is often mentioned with heroic confidence and insufficient budgeting. Changing a planet's air is not like adjusting a thermostat. Earth's own breathable atmosphere did not appear overnight. Early Earth likely had little free oxygen. For much of our planet's history, oxygen was scarce. Then photosynthetic microbes, especially cyanobacteria, slowly began releasing oxygen as a byproduct. Over immense spans of time, this transformed oceans, rocks, and atmosphere in what is often called the Great Oxidation Event. In other words, the breathable air we take for granted was produced by life changing the planet. That is a profound idea. We often think life adapts to planets, but life also modifies them. Forests, plankton, soils, wetlands, and microbes continue participating in atmospheric balance today. Plants produce oxygen, though the long-term story is linked to carbon burial and geochemical cycles more complex than the average houseplant biography suggests. Oceans absorb gases, volcanoes emit them, weathering removes some, climate feeds back into chemistry. Air is not just present, it is maintained. That may mean breathable atmospheres are rarer than simply rocky planet in the right zone. A world may need active geology, liquid water, long-term stability, magnetic shielding perhaps, and maybe biology itself helping shape conditions. We do not yet know how common that combination is. When astronomers study exoplanets, one major goal is atmospheric detection. By observing starlight filtering through a planet's atmosphere during transit, Scientists can infer certain gases. It is astonishing work. We cannot visit these worlds, yet we can sometimes estimate what surrounds them from many light years away. Still, caution is essential. Oxygen alone is exciting but not conclusive. It can arise through non-biological processes under some conditions. Methane plus oxygen together may be more interesting because they tend to react away unless replenished. Context matters. Star type matters. Surface chemistry matters. The universe rarely hands out simple answers. There is also the issue of gravity. On a low-gravity world, atmospheres escape more easily over geological time unless replenished or protected. Mars is a familiar example. It once had a thicker atmosphere and flowing water, but much was lost. On a higher gravity world, dense atmospheres may be easier to retain, but surface pressure could become uncomfortable or dangerous depending on composition. Again, balance, a phrase we may return to often. If all this sounds like a lot of conditions for one humble breath, that is because it is. Every easy inhale on Earth represents countless invisible compatibilities. Your lungs evolved here. Your blood chemistry expects this place. Your enzymes, tissues, temperature regulation and nervous system all assume this atmospheric partnership. You are, in a sense, locally optimized. That should make us more impressed by ordinary breathing than we usually are. Take a slow breath now if you like. Nothing dramatic. No need to turn it into a lifestyle movement. Just notice how effortless it can be when conditions cooperate. Air enters, oxygen diffuses, carbon dioxide leaves, heartbeat continues, thoughts continue wandering about groceries and galaxies. No alarms, no suit required. This is what another truly breathable world would need to offer. Not merely survivability, but ease. Not just a desperate gasp made possible by numbers on a chart, but the casual freedom to walk outdoors and forget the atmosphere again. That may be the highest compliment a planet can receive, to be so hospitable that no one thinks about it. Yet even on Earth, breathable does not mean uniform. Cities with pollution can harm lungs. Wildfire smoke can turn familiar air dangerous. Indoor spaces with poor ventilation can concentrate contaminants. Allergens drift. Humidity changes comfort. Heat waves strain breathing. The same atmosphere that sustains us can be locally compromised by natural events, or our own behaviour. So perhaps the question is not only whether other planets have breathable air, it is whether we understand and value breathable air anywhere. Because if we someday find another world with skies we can safely stand beneath, we will recognise its worth instantly. But we already live under one now, and often notice it only when it is threatened. That is a very human habit. Step outside on an ordinary day, and it may not feel like you are participating in one of the great successes of planetary history. It may feel like you are checking the mail, taking the bins out, wondering why the neighbour's dog has chosen this exact moment to express itself so passionately, or deciding whether the jacket was a mistake. Daily life has a talent for disguising miracles as routine, yet every comfortable breath you take is made possible by an atmosphere so unusually cooperative that the more closely we study other worlds, the more remarkable our own begins to look. Earth's atmosphere is kind in a very practical sense. It does not usually poison us, crush us, freeze us, cook us, strip us with radiation, or require us to carry tanks and hoses merely to stroll outside. That may sound like faint praise, but in a universe where many places would do several of those things at once, it is extraordinary. When we ask whether there are other planets we can breathe on, we are often imagining a world like ours. But to understand how difficult that may be to find, we first need to understand how much had to go right here. Because Earth did not begin as a gentle blue sanctuary with birdsong and agreeable breezes. Early Earth was rough company. More than 4 billion years ago, the young planet was hot, violent, frequently struck by debris, geologically restless, and wrapped in an atmosphere very different from today's. There was little or no free oxygen to speak of. Volcanoes likely released water vapour, carbon dioxide, nitrogen, sulfur compounds, and other gases into the sky. The surface was transforming constantly. Oceans eventually formed, continents slowly assembled and broke apart. The planet was not finished, it was under loud construction. If a modern human had somehow visited that ancient Earth, they would not have admired the rustic charm. They would have died promptly and with considerable confusion, so the first lesson is simple. A breathable atmosphere is not the default setting of rocky planets. It is a later achievement. Many worlds may form, far fewer may mature gracefully. One of Earth's great advantages is its location around the Sun. We orbit within a range where liquid water can persist on the surface under suitable conditions. Too close, and water risks boiling away or runaway greenhouse heating. Too far, and it freezes extensively. This region is often called the habitable zone, though the name can be a bit optimistic. Being in the zone does not guarantee comfort any more than owning gym shoes guarantees fitness. Still, Earth occupies valuable real estate. Liquid water matters because water is not only useful for life, it also helps regulate climate, shape geology, transport chemicals, and participate in the carbon cycle. Oceans store heat, moderate temperatures, dissolve gases, and support ecosystems that themselves influence atmospheric chemistry. Rain erodes rock, weathering minerals that can lock away carbon dioxide over long timescales. Rivers move nutrients, ice reflects sunlight, clouds alter heating and cooling. Water does not merely sit there looking photogenic, it works. Then there is the size of Earth. A planet too small struggles to hold onto an atmosphere over geological time. Its gravity is weaker, making it easier for lighter gases to escape into space. It may also cool internally faster, reducing volcanic activity and magnetic protection sooner. Mars offers a familiar cautionary tale. Once wetter and thicker aired, it lost much of what made it potentially more temperate. A planet too large may hold thick atmospheres more easily, but those atmospheres can become dense, crushing, or chemically strange depending on composition and history. Earth, once again, seems to occupy a favourable middle ground. This pattern repeats so often it begins to feel suspicious. Another important gift lies beneath our feet, a still active interior. Earth's core and mantle drive plate tectonics, volcanism, and long-term recycling of material between crust, oceans, and atmosphere. Continents move, seafloors spread, carbon locked in rocks can eventually return through volcanic processes. New crust forms, old crust sinks, mountains rise and erode. Plate tectonics is messy, dramatic, and occasionally rude to cities, but it may be crucial for long-term habitability. Why? Because climates drift. Stars change brightness over time. Chemical imbalances emerge. A planet needs ways to respond. Earth has one. The carbon silicate cycle acts as a planetary thermostat over immense timescales. If Earth becomes warmer, increased weathering can remove more carbon dioxide from the atmosphere, gradually cooling things. If Earth cools too much, weathering slows while volcanic emissions continue, allowing carbon dioxide to build and warm the planet. It is not a neat household thermostat with buttons and polite efficiency. It is more like a geological committee working very slowly across millions of years, but it functions. Without such feedbacks, climates can run away into extremes. Venus may be an example of what happens when matters go badly. Similar in size to Earth, Venus likely once had more temperate conditions, perhaps even oceans long ago. Today it is wrapped in a dense carbon dioxide atmosphere, with surface temperatures hot enough to melt lead, pressures crushing enough to flatten optimism, and clouds of sulfuric acid for style. Same neighbourhood, very different outcome. That should humble us. Earth also benefits from a magnetic field generated by motions in its liquid outer core. This field extends into space and helps deflect charged particles from the solar wind. It is not an impenetrable shield, but it reduces atmospheric stripping and radiation exposure. Without magnetic protection, a star's energetic particles can gradually erode atmospheres, especially on smaller worlds. Mars again serves as a warning. Its global magnetic field faded long ago. Combined with low gravity, this likely contributed to atmospheric loss. We sometimes picture atmospheres as permanent blankets. In reality, stars tug at them, chemistry alters them, gravity leaks them, impacts disturb them, and time tests them. Earth has held on admirably. But perhaps the most astonishing ingredient in our breathable sky is life itself. For a long stretch of Earth's early history, free oxygen remained scarce. Then tiny organisms changed everything. Cyanobacteria and other photosynthetic microbes use sunlight to split water and release oxygen. At first, that oxygen reacted with dissolved iron and other materials. Only after those sinks were saturated did oxygen begin accumulating significantly in the atmosphere. This transition, often called the Great Oxidation Event, transformed the planet. To many anaerobic organisms, oxygen was toxic. For future complex life, it became opportunity. High-energy metabolism using oxygen supports larger, more active, more complex organisms. Over time, multicellular life diversified. Eventually forests spread, marine ecosystems flourished, insects buzzed, reptiles wandered, mammals fussed, and humans invented meetings. All because microbes altered the air. That idea deserves repeating. Earth's atmosphere is kind partly because life made it so. This means that when we search for breathable planets elsewhere, we may not simply be searching for suitable rocks. We may be searching for worlds where biology and geology have entered a long productive partnership, and partnerships are harder to predict than rocks. Even today, the atmosphere remains dynamic. Plants and plankton contribute oxygen production. Respiration consumes oxygen. Carbon moves between air, oceans, soils, and living tissue. Wetlands emit methane. Forest loss changes regional climate and gas balance. Ocean warming alters absorption patterns. Dust from one continent fertilizes ecosystems on another. The sky above you is tied to roots, microbes, currents, and stone. It only looks empty. Its composition is also conveniently moderate. Roughly 21% oxygen is enough to support active animal life, while avoiding some hazards of much higher concentrations. Geological evidence suggests that oxygen levels have varied through history, sometimes higher than today. During certain periods, elevated oxygen may have helped giant insects thrive, because diffusion through their respiratory systems became easier. Interesting for documentaries, less ideal if dragonfly traffic increases. Too much oxygen can intensify wildfire behavior and oxidative stress. Too little constrains complex metabolism. Once more, Earth seems to inhabit a comfortable range. Nitrogen, the majority gas, provides pressure and stability while being comparatively inert. Carbon dioxide exists in small amounts, enough to help trap heat but not enough, under natural pre-industrial conditions to create Venus-like disaster. Water vapour varies and contributes to weather and greenhouse warming. Everything interacts. This is why describing Earth's atmosphere as air can undersell it badly. It is a tuned mixture maintained by ongoing processes. Not static ingredients in a jar, but a living system. Then there is the Moon. Our large moon likely formed from a giant impact early in Earth's history. Beyond providing tides and poetry, it stabilizes Earth's axial tilt over long periods. A relatively stable tilt helps moderate climate patterns and seasonal regularity. Without such stabilization, a planet's tilt might vary chaotically, potentially causing severe long-term climate swings. Even our nightlight appears to have been useful. Some scientists debate exactly how crucial each factor is, and caution is wise. Nature often surprises us with multiple paths to similar outcomes. Still, Earth appears to possess an impressive collection of advantages gathered in one place. Right star type, useful orbital distance, persistent liquid water, appropriate mass, long-lived geology, magnetic shielding, climate feedback systems, life capable of transforming the atmosphere, relative long-term stability. That is quite a resume. No single feature guarantees habitability. Together, they create resilience, and resilience may be rarer than initial habitability. A world might be pleasant for 10 million years and then fail dramatically. Stars brighten over time, interiors cool, magnetic fields weaken, impacts occur, atmospheric chemistry shifts, oceans escape, greenhouse states emerge. Earth has remained suitable for billions of years, despite ice ages, mass extinctions, asteroid impacts, volcanic cataclysms, and several moments when life itself might reasonably have requested a break. That long continuity matters because complex life takes time. Single-celled organisms appeared relatively early. Intelligent tool-using creatures who argue online required considerably more patience. If breathable atmospheres flicker briefly and vanish, many planets may never host advanced observers capable of appreciating sunsets or mishandling email. This brings us to a subtle point. Earth's atmosphere feels kind because we are adapted to it. Had life evolved differently under different chemistry, another atmosphere might feel normal to its natives and hostile to us. Kind is partly human-centered. Yet within human limits, Earth truly is exceptional. We can walk outside almost anywhere with no breathing equipment. Even in deserts, mountains, forests, cities, coastlines, and tundra, the same basic atmosphere supports us. Conditions vary, but the sky remains broadly usable. That portability of human life across one planet is remarkable. Imagine if crossing a continent required changing lung hardware. We complain about humidity instead. Of course, Earth's kindness is not unconditional. Hurricanes, droughts, blizzards, heat waves, smoke, pollution, and disease remind us that hospitable does not mean harmless. Nature can be stern while still being habitable. But compared with most known alternatives, our atmosphere is generous. It lets billions of people live outdoors daily with minimal thought. The more astronomy reveals, the more precious that seems. Thousands of exoplanets have now been discovered. Some may be rocky, some may orbit within temperate zones, some may hold atmospheres. Yet distance makes certainty difficult. We infer masses, radii, orbital periods, starlight signatures. We estimate. We model. We hope. What we know directly, intimately, continuously, is one breathable world. This one. That perspective can change the tone of exploration. Searching for other habitable planets should inspire wonder, but also responsibility. If Earth's atmosphere is unusually kind, then damaging it casually becomes less like scratching cheap furniture and more like vandalizing a rare masterpiece. A masterpiece that also happens to keep us conscious. And perhaps that is the practical lesson hidden inside cosmic curiosity. Looking outward teaches inward gratitude. When we imagine other skies, we notice our own. When we ask whether another planet can sustain us, we begin to understand how much this one already does. Take a slow breath, and something extraordinary begins without asking for your attention. Air moves through the nose or mouth, down the throat through branching tubes, into smaller and smaller passages until it reaches millions of tiny sacs deep in the lungs. Their walls are astonishingly thin. On one side sits the atmosphere, on the other, blood. Between them lies one of the most important exchanges in your life, repeated every few seconds since birth. Oxygen enters, carbon dioxide leaves. You do not need to supervise it. No daily checklist is required. There is no button marked "continue respiration." It simply happens, hour after hour, through sleep, stress, laughter, boredom, and every awkward conversation you have ever survived. Because breathing feels so automatic, it is easy to assume it is simple. In reality, it depends on chemistry, physics, anatomy, and balance so precise that moving to another planet becomes far more complicated than merely finding air. We often talk as though lungs are bellows and oxygen is fuel poured directly into the body. It is a useful shorthand, but the real story is subtler. Your lungs do not burn oxygen like a furnace. They deliver it to blood, which carries it to cells, where oxygen helps unlock energy from food through controlled biochemical processes. You're less a candle and more a carefully managed power station with opinions. Let us begin with oxygen itself. Oxygen is highly reactive. That reactivity is why it is so useful. Inside cells, oxygen helps extract energy from molecules derived from food. Sugars, fats, and proteins are broken down through pathways that ultimately allow cells to produce ATP, the molecular energy currency used for movement, repair, signaling, transport, and the countless expensive habits of living tissue. Without enough oxygen, this system falters quickly. Brains are especially demanding. Though small in mass relative to the body, the brain consumes a great deal of oxygen. Interrupt supply for even a few minutes and serious damage can occur. Muscles weaken. Thinking becomes confused. Coordination declines. Decision-making suffers, which is unfortunate because that is precisely when good decisions would help most. Yet oxygen is not simply more is better. Too little oxygen is dangerous. Too much oxygen over time can also damage tissues. Oxygen's reactive nature can produce harmful molecules known as reactive oxygen species. Normally the body manages these with antioxidant systems, but excess exposure can overwhelm defences. So the ideal atmosphere is not one overflowing with oxygen like an enthusiastic sales pitch. It is one with enough in the right context. That phrase, in the right context, matters enormously. Suppose a planet had an atmosphere containing 21% oxygen, the same rough fraction as Earth. Sounds promising. We begin browsing alien property listings, but percentages alone can mislead. What matters for breathing is partial pressure. Partial pressure is the share of total pressure contributed by a specific gas. If total atmospheric pressure changes, the effective availability of oxygen changes even if the percentage remains identical. Here on Earth at sea level, the total pressure is high enough that oxygen molecules are sufficiently abundant and forceful, if you like, to diffuse efficiently from lung air into blood. At high altitude, the percentage of oxygen remains similar, but total pressure falls. That means oxygen partial pressure falls too. The result? You breathe the same recipe, but a weaker serving. This is why mountains can humble confident people very quickly. Climbers ascending high peaks often experience headache, fatigue, nausea, dizziness, disturbed sleep, poor judgment, and dangerous altitude illnesses. The lungs are still receiving air. They are simply receiving air whose oxygen is spread too thinly. Imagine trying to pay rent using the correct currency, but only half the amount. Now, reverse the situation. A denser atmosphere with lower oxygen percentage might still provide adequate oxygen if total pressure were high enough. Again, context. That means another world could technically support breathing with an unfamiliar gas mix, while a seemingly Earth-like composition at the wrong pressure could fail dramatically. Space, as usual, refuses shortcuts. Pressure influences more than oxygen uptake. If pressure is extremely low, body fluids can begin behaving in troubling ways. Water boils at lower temperatures under lower pressure. In near vacuum, exposed tissues face severe problems rapidly. This is why spacesuits are not fashion statements, though some are admittedly sleek. High pressure creates different issues. Dense atmospheres can strain breathing mechanics, alter gas behavior, and cause physiological complications. Divers know some of these challenges underwater, where increased pressure affects how gases dissolve in the body. Nitrogen narcosis, oxygen toxicity at certain partial pressures, and decompression sickness all emerge from pressure interacting with chemistry. The body likes moderation more than adventure. Let us talk about hemoglobin, one of the quieter heroes in this story. Hemoglobin is a protein in red blood cells that binds oxygen in the lungs and releases it in tissues. Its behaviour is elegant. It loads oxygen where oxygen concentration is high and unloads more readily where tissues need it. Carbon dioxide levels, acidity, temperature and other factors help tune this process. Your blood is not merely carrying cargo, it is negotiating delivery terms constantly. This system also explains why carbon monoxide is so dangerous. Carbon monoxide binds to hemoglobin far more strongly than oxygen does. Even small amounts can occupy binding sites and reduce oxygen transport. A person may be surrounded by breathable-looking air and still suffocate at the cellular level. It is one of the crueler tricks in chemistry. Carbon dioxide, meanwhile, deserves more respect than it usually receives. We think of it as waste gas, and it is, but it also helps regulate breathing. Rising carbon dioxide levels in blood change acidity and stimulate the urge to breathe. Many people assume low oxygen is the main trigger to inhale, but carbon dioxide buildup is a major signal. Your body is often less concerned with adding oxygen than removing yesterday's metabolic paperwork. If surrounding air contains too much carbon dioxide, trouble arrives fast. The body struggles to expel enough of it. Headaches, panic, confusion, elevated heart rate, impaired thinking, unconsciousness, and death can follow depending on concentration and exposure time. So when we evaluate alien atmospheres, oxygen presence alone is nowhere near enough. We must ask what else is mixed in. Nitrogen, which makes up most of Earth's atmosphere, is relatively inert under ordinary conditions. It acts as a stable background gas and contributes pressure. Useful, calm, dependable nitrogen. The sensible colleague of the atmosphere, argon is also mostly harmless in normal amounts. Water vapour affects comfort, heat retention, and weather. Carbon dioxide in modest amounts helps warm the planet, but in large amounts creates breathing and climate problems. Then there are gases humans would rather avoid. Hydrogen sulfide can interfere with cellular respiration and is toxic. Sulfur dioxide irritates lungs, chlorine damages tissues, ammonia burns and harms. Methane may not be highly toxic in low amounts, but a methane-rich atmosphere usually implies an overall environment not tailored to human convenience. Even if chemistry is acceptable, particles matter. Dust, smoke, spores, salts, volcanic ash, and aerosols can inflame airways or scar lungs. Imagine a planet with excellent gas composition, but constant airborne microscopic glass shards from active volcanism. Technically breathable becomes emotionally contested. Temperature adds another layer. Cold dry air can irritate airways and increase stress on the body. Extremely hot air can damage tissues and impair cooling. Humidity changes how efficiently sweat evaporates, which affects heat management. Humans regulate body temperature partly through evaporation, and atmospheres that disrupt this can become dangerous even if gases are otherwise fine. So a safe breath is not one variable, it is a whole arrangement. This arrangement continues inside the lungs themselves. Human lungs contain branching airways ending in roughly hundreds of millions of alveoli, tiny sacs providing enormous surface area for gas exchange. If spread flat, that surface area would be surprisingly large. Evolution has packed a chemical trading floor into your chest. The alveolar walls are thin, moist, and closely wrapped with capillaries. Oxygen dissolves into this moist layer, crosses membranes, enters blood, binds hemoglobin. Carbon dioxide moves the other way. Every step depends on gradients. Molecules move from regions of higher partial pressure to lower. If gradients weaken, exchange weakens. If membranes thicken through disease or fluid buildup, exchange worsens. If circulation falters, delivery suffers. Breathing is simple only from the outside. This is why illnesses such as pneumonia, pulmonary edema, fibrosis, asthma, and emphysema can be serious. They disrupt the mechanics or chemistry of exchange. Air may still enter lungs, but efficient transfer is compromised. Again, inhaling is not the same as receiving oxygen. Now imagine transplanting this delicate Earth-evolved system to another planet. Perhaps gravity is higher, making chest expansion harder over time. Perhaps atmospheric density changes airflow resistance. Perhaps local allergens trigger inflammation. Perhaps trace gases slowly injure tissues. Perhaps day-night temperature swings stress physiology. Perhaps microbial life, if present, interacts unpredictably with immune systems. Even a nearly breathable world might still require adaptation, filters, medicine, or enclosed habitats. Humans already show some flexibility, of course. Populations living at altitude have developed useful physiological traits over generations. People acclimatise by increasing ventilation and red blood cell production. Athletes train in low-oxygen environments seeking performance benefits. Divers adapt to pressure protocols. Pilots use oxygen systems. We are capable, but not infinitely so. There is a reason mountaintops are climbed, not densely urbanised. Another fascinating point is that Earth's oxygen level has changed over geological time. It has not always sat near modern values. During some ancient periods, oxygen rose substantially higher. This may have supported giant insects because diffusion through their respiratory systems became easier. However, higher oxygen also increases fire intensity. A forest in a high oxygen world may become dramatically more flammable. Every atmospheric gift arrives with trade-offs. If oxygen fell significantly below modern levels, complex active animals would face constraints. Endurance drops. Cognitive performance suffers. Ecosystems shift. Fire behaviour changes in the opposite direction. Evolution might take other routes, but human civilization built around current air would not enjoy the transition. This should make us appreciate how narrow many comfortable ranges really are. We often imagine life as robust, and in many ways it is. Microbes thrive in boiling vents, acidic pools, deep rock, frozen brine, and radiation-rich environments. But human comfort is a narrower niche than life itself. There may be many living worlds that are not human-breathing worlds. That distinction is essential. When astronomers detect oxygen in an exoplanet atmosphere, headlines become excited. Understandably so. Yet oxygen is only one clue. It could arise from life, or from non-biological processes such as water loss under intense starlight leaving oxygen behind. The total pressure may be wrong. Other toxic gases may dominate. Surface temperatures may be severe. A distant spectral line does not guarantee pleasant hikes. Still, it is a clue worth following. Because somewhere, perhaps, there may be a world where pressure is moderate, oxygen available, toxins scarce, temperatures tolerable, and chemistry stable enough for a person to step outside and simply breathe. But even then, breathing may not equal thriving. Nutrition, pathogens, gravity, psychology, day length, radiation, and countless ecological details would remain. The first breath would be only the beginning. There is also a quiet philosophical lesson here. The ordinary inhale you take without gratitude depends on balances so intricate that reproducing them elsewhere may be among the hardest things our species ever attempts. The sky above you is not empty convenience. It is a finely tuned interface between biology and planet. Take another slow breath now. Nitrogen providing pressure, oxygen crossing membranes, hemoglobin loading and unloading, carbon dioxide leaving, diaphragm moving, heart coordinating deliveries, cells receiving supplies they requested rudely seconds ago. All of this happening with no applause. Perhaps that is why Earth feels so generous. It supports impossibly complex chemistry and then presents it as background normality. At first glance, it sounds like an upgrade. Imagine hearing that a newly discovered planet has more oxygen than Earth. Instantly, the mind begins making cheerful assumptions. More oxygen must mean easier breathing, stronger bodies, greater stamina, Perhaps a world where jogging upstairs feels vaguely heroic rather than personally insulting. It sounds like the atmospheric equivalent of finding extra legroom on a flight. Surely more of the thing we need must be better. And yet biology has a long history of disappointing simple logic. The truth is that oxygen is one of those substances that becomes dangerous the moment we mistake usefulness for harmlessness. We need it constantly. We cannot survive long without it. But oxygen is also chemically aggressive, highly reactive, and entirely capable of causing trouble when present in excess. A planet with significantly more oxygen than Earth might support life of some kinds, but whether it would comfortably support humans is a much more complicated question. Once again, the universe declines to offer freebies. Let us begin with Earth, where oxygen makes up about 21% of the atmosphere. That number can feel ordinary because it is familiar, but familiarity should not be confused with inevitability. Earth's current level is the result of long planetary history, biological activity, geology, burial of carbon, ocean chemistry, and countless feedback loops. It is not a random percentage. It is the latest version of a system still changing slowly over time. If oxygen were much lower, complex active animals like us would struggle. If oxygen were much higher, different problems emerge. To understand why, it helps to remember what oxygen actually does. Inside the body, oxygen helps cells extract energy efficiently from food. That efficiency supports brains, muscles, movement, warmth, and all the expensive habits of multicellular life. But oxygen's usefulness comes from its reactivity. It participates eagerly in chemical reactions. That same eagerness can damage living tissue. Cells naturally generate reactive oxygen species during metabolism. Under normal conditions, the body manages these molecules using antioxidant defenses and repair systems. A certain amount of oxidative stress is routine. Life is accustomed to it. But increase oxygen exposure too far and the balance can tip. Too much oxygen can injure lungs, irritate airways, damage delicate tissues, affect the nervous system, and increase long-term cellular stress. In medical settings, high concentration oxygen is valuable treatment when used appropriately, but prolonged exposure is monitored carefully because more is not automatically safer. This surprises many people. We tend to think of oxygen as the hero gas, arriving dramatically to save the day. In reality, oxygen is more like a powerful employee who performs brilliantly but requires supervision. Now imagine an entire planet where atmospheric oxygen levels are significantly above Earth's. Would you feel amazing stepping outside? Perhaps briefly, perhaps not at all. It depends on how much higher, what the total atmospheric pressure is, and what other gases are present. As always, percentages alone are sneaky. If oxygen concentration rose moderately, say somewhat above Earth levels, some people might initially notice easier oxygenation during exertion, especially if pressure were also favourable, but over time the body would respond. Human physiology is designed around current Earth norms. Systems regulating breathing, blood chemistry, circulation and oxidative balance evolved here, not in some hyperoxygenated paradise. And if oxygen levels rose substantially, risks could outweigh benefits quickly. Lung tissues are delicate. The surfaces where oxygen passes into blood are thin, moist and biologically active. High oxygen exposure can inflame and damage these structures. Prolonged breathing of elevated oxygen concentrations may reduce lung function, cause chest discomfort, coughing, and more severe complications depending on level and duration. Your lungs are excellent at handling ordinary life, but they prefer moderation. There is another issue less discussed but wonderfully dramatic: fire. Higher oxygen atmospheres make combustion easier, materials ignite more readily, flames burn hotter, and spread faster. Things that smoulder on Earth might blaze enthusiastically elsewhere. Wildfires could be more frequent or intense depending on vegetation, climate and ignition sources. Industrial safety becomes more challenging. A dropped spark may become a local event. Even everyday materials can behave differently in oxygen-rich environments. Fabrics, oils, dusts, and machinery that seem manageable here may become more hazardous there. Engineers become very attentive under such conditions. So if you dreamed of cozy cabin life on a lush oxygen world, do keep an eye on the toaster. Earth itself offers clues. Geological evidence suggests atmospheric oxygen has varied considerably across deep time. During the Carboniferous period, roughly 300 million years ago, oxygen levels may have risen substantially above today's, perhaps around the low to mid 30% range, though estimates vary. That world was strange and fascinating. Large forests spread across swampy landscapes. Enormous insects and arthropods existed, including giant dragonfly-like creatures with wingspans far larger than modern insects. One proposed reason involves oxygen. Insects rely on a tracheal system where gases diffuse through tubes, rather than being pumped by lungs like ours. Higher atmospheric oxygen may have helped support larger body sizes by making diffusion more effective. So yes, a high oxygen world might have impressive bugs. This may influence some people's relocation plans. Wildfire evidence from ancient sediments also suggests that higher oxygen made fires easier to sustain. There appears to be a relationship between oxygen levels and how readily landscapes burn. Too low and fires struggle. Higher and they become more common. Thus, a lush forest planet with abundant oxygen might also be a planet where forests periodically become excellent arguments for caution. Would humans adapt over generations to such an atmosphere? Possibly to some extent. Biology is flexible within limits. Populations adapt to altitude, climate, diet, and disease pressures. But rapid relocation to a significantly different oxygen world would not be trivial. Long-term residence might require environmental controls, selective habitat design, or gradual physiological adaptation. In practice, future settlers might choose to live inside controlled spaces even if the outside air is technically breathable. That phrase matters, technically breathable. There is a difference between surviving an atmosphere and flourishing in it. Humans can survive high mountains, deserts, polar regions, submarines, aircraft cabins, and cramped offices with suspicious ventilation. Survival does not equal ideal living conditions. Another complication is pressure. Suppose a planet had 30% oxygen but low total atmospheric pressure. The actual oxygen partial pressure might resemble Earth's or only slightly exceed it. In that case, breathing could be more manageable than the raw percentage suggests. Now suppose the same 30% oxygen existed in a dense high-pressure atmosphere. That could produce much higher oxygen partial pressures, increasing physiological risks. This is why planetary brochures should always include the fine print. What about athletic performance? Would a higher oxygen world create naturally stronger humans? Perhaps some short-term endurance tasks would feel easier if oxygen delivery improved modestly. Athletes sometimes train or recover with supplemental oxygen under controlled conditions. But beyond certain ranges, the benefits plateau and harms rise. Muscles are not magic sponges that simply improve forever with more oxygen. Performance depends on cardiovascular systems, heat management, gravity, nutrition, biomechanics, sleep, training, and whether one remembered to stretch. A planet with higher gravity might erase any oxygen advantage by making movement exhausting. A world with toxic pollen the size of coins might also interfere. Never trust a single metric. There is also the question of evolution. If a planet naturally maintained higher oxygen over long spans, native life might differ dramatically from Earth's. Larger insects are one possibility if similar respiratory constraints evolved. Metabolisms could run differently. Fire ecology would shape plant strategies. Antioxidant systems might be stronger. Tissues may be built for a chemistry humans are not. We often imagine ourselves arriving as the standard of comparison. Nature may disagree. Could intelligent life evolve there? Quite possibly. Different does not mean impossible. but it might be adapted to conditions that make human settlement inconvenient. Perhaps their version of hospitality includes handing visitors flame-retardant clothing and a breathing schedule. Then there is the source of the oxygen itself. Free oxygen is reactive and tends not to remain abundant without replenishment. On Earth, photosynthetic life continually contributes to maintaining atmospheric oxygen over long timescales. If another world had high oxygen, scientists would immediately ask why. Is life producing it? Is water being split by intense radiation with hydrogen escaping to space? Is geology involved? Is the atmosphere stable or temporary? Because an oxygen-rich atmosphere can sometimes indicate not paradise, but imbalance. For example, if a planet lost large amounts of water due to stellar heating, hydrogen might escape while oxygen accumulates. That could leave plenty of oxygen, but not necessarily oceans, ecosystems, or friendly conditions. You might find breathable chemistry in a deeply unpleasant context. This seems to be a recurring theme in astronomy. Suppose future explorers discover a planet with slightly elevated oxygen, moderate pressure, Earth-like gravity, liquid water, and tolerable temperatures. That would be exciting indeed. But would they simply walk outside and live normally? Likely not immediately. Microbes, allergens, unknown biochemistry, trace gases, ultraviolet radiation, weather patterns, and food chain incompatibilities would all matter. Human settlements would probably begin with filtered habitats, medical monitoring, and many committees. The first person to say, "It smells fine, let's just go," would concern everyone else. There is also a psychological angle. We often equate abundance with safety. More water, more fuel, more oxygen. Yet ecosystems thrive on balance, not maximum values. The body does too. Blood sugar, temperature, salt levels, hormone levels, hydration, pH pressure, and oxygen all function within ranges. Push them too far either direction, and trouble begins. Life is not optimized for excess, it is optimized for control. That may be one reason Earth feels so comfortable. Our atmosphere sits within workable limits shaped by billions of years of feedback. Enough oxygen for energetic life. Not so much that forests ignite because someone sneezed near dry leaves. Enough density for breathing and weather. Not so much that the air itself feels heavy and crushing. Again, our planet appears suspiciously sensible. Would children born on a higher oxygen world develop differently? Possibly. Growth patterns, oxidative stress exposure, disease risks, and developmental physiology could all shift depending on actual conditions, but such questions remain speculative. We do not have colonies of toddlers on exoplanets yet, though one suspects they would adapt faster than the adults and complain less. Adults would mostly discuss paperwork. Another practical note: spacecraft and habitats already teach us caution with oxygen. High oxygen environments can increase fire danger. The tragic Apollo 1 cabin fire remains a sobering reminder of how dangerous enriched oxygen settings can be under the wrong conditions. Engineers since then have treated atmospheric design with great seriousness, because air is not empty space, it is chemistry you live inside. That may be the central lesson of this entire topic. So could we survive on a planet with more oxygen than Earth? Possibly, under some ranges and with the right total pressure, climate and supporting conditions. Would it automatically be better than Earth? Almost certainly not. Could it be worse in surprising ways? Very much so. The dream of more oxygen equals more life is tempting, but reality prefers nuance. A modest increase might be manageable or even advantageous in some respects. A large increase could damage lungs, increase fire risk, alter ecosystems, and create constant hazards. As ever, the perfect breath lies not in abundance but in proportion. Take a slow inhale now from the ordinary atmosphere around you. 21% oxygen, give or take, balanced by nitrogen and moderated by planetary systems older than mountains in their current form. Not flashy, not maximal, not dramatic, just quietly suitable. And suitability may be the rarest luxury of all. Now let us consider the opposite kind of disappointment. A planet may look solid, scenic, and even strangely inviting from orbit. There may be canyons, plains, mountains, frost, clouds, dust, shadows, perhaps the glint of ice. Yet if you stepped onto its surface without protection, the first thing you would notice is not the view. It would be the absence, not silence in the poetic sense, though that would come too, not loneliness, though there might be plenty of that. The real shock would be the absence of enough air, too little pressure, too few molecules pressing back against your lungs, too little atmosphere to support the ordinary act that Earth lets you forget every minute of your life. Breathing. We often imagine danger as something active. Flames, toxins, storms, claws, lasers, if cinema has had any say in the matter. But some worlds are dangerous because they are missing something rather than adding something. No poison required, no dramatic monster necessary, just an atmosphere too thin to help you live. That kind of danger can be strangely elegant. On Earth, we live at the bottom of a vast ocean of air. The atmosphere presses downward with weight. At sea level, every square centimetre of your body experiences pressure from countless gas molecules moving and colliding constantly. You do not feel crushed because your body is adapted to this pressure and balanced internally. It feels normal because it has always been normal to you. But remove enough of that pressure, and normal begins to unravel. As we explored earlier, lungs do not simply need oxygen present in theory. They need enough oxygen partial pressure to move oxygen from inhaled air into blood. If atmospheric pressure drops too low, breathing becomes increasingly difficult even if oxygen exists as a fraction of the atmosphere. There are simply too few useful molecules arriving per breath. This is why altitude matters on Earth. At high mountain elevations, climbers face thinner air. Oxygen percentage remains broadly similar, but total pressure falls. Many people feel short of breath, fatigued, lightheaded and slow. Push high enough, and survival becomes precarious without acclimatization or supplemental oxygen. Now imagine taking that mountain experience and making it permanent. Then removing even more air. Welcome to thin atmosphere worlds. The most famous example, of course, is Mars. Mars is often described as Earth's cousin, neighbour, backup plan, future destination, and occasionally by people selling books, our inevitable second home. It is a fascinating world and one of the best places to study planetary habitability. But Mars today has an atmosphere so thin that surface pressure averages less than 1% of Earth's sea level pressure. That is not a bit breezy, that is profoundly sparse. Its atmosphere is composed mostly of carbon dioxide, with small amounts of nitrogen and argon. Even if the chemistry were kinder, the pressure alone creates major problems. Liquid water is unstable at the surface under many conditions. Human lungs cannot extract usable oxygen unaided. Exposure without a pressure suit would be rapidly dangerous. Mars offers dramatic landscapes, ancient river valleys, polar caps, giant volcanoes, and dust storms the size of continents. It does not offer casual outdoor breathing. The thin Martian atmosphere also means weak sound transmission compared with Earth. NASA's rovers have recorded wind and mechanical sounds there, but everything behaves differently. The air carries less, softens less, supports less. It is a reminder that atmosphere is not merely for lungs. It shapes weather, sound, erosion, temperature, and daily experience. Mars likely once had a thicker atmosphere. Billions of years ago, rivers flowed and lakes existed. Something changed. Low gravity, loss of global magnetic shielding, solar wind stripping, chemical sequestration, and time all played roles in thinning the envelope of air. Mars is a world where habitability may have faded. That alone makes it poignant. Another famous example is Mercury. Mercury sits much closer to the Sun and is often called nearly airless. Technically, it has an exosphere rather than a substantial atmosphere. An exosphere is an extremely tenuous collection of atoms and molecules so sparse they rarely collide. Mercury's exosphere contains traces of oxygen, sodium, hydrogen, helium, potassium, and other particles supplied by solar wind interactions, surface sputtering, and micrometeorite impacts. If that sounds scientifically interesting but personally unhelpful, that is correct. Mercury's air is far too thin to breathe, far too thin to weather landscapes in familiar ways, and far too thin to moderate temperature. As a result, Mercury experiences savage day-night contrasts. Sunlit regions can become extremely hot, while nighttime temperatures plunge dramatically. Without a real atmosphere, there is little blanket, little cushion, little conversation between surface and sky. Just exposure. Then we have Earth's own companion, Moon. The Moon also possesses an exosphere, extraordinarily tenuous and composed of atoms such as helium, neon, argon, sodium, and potassium. For practical human purposes, the Moon is airless. No breathable pressure, no wind in the ordinary sense, no weather as we know it. Footprints can remain for immense spans because there is no rain or moving air to erase them. Stand on the Moon unprotected, and the problem is not that the air is bad, it is that the air is absent. This absence affects everything. Dust behaves differently. Heat transfer changes. Sound does not travel through vacuum between people standing apart. A hammer and feather fall together in the absence of atmospheric drag, as famously demonstrated. The Moon is not hostile through aggression. It is hostile through indifference. Let us move beyond our solar system. Many exoplanets known to science may also have thin or vanished atmospheres, though direct certainty can be difficult. One especially well-known world is Proxima Centauri b, orbiting the nearest star to the Sun, Proxima Centauri. This planet receives enormous attention because it lies in a region where liquid water might be possible depending on atmospheric conditions. But there is a complication. Red dwarf stars like Proxima Centauri can be magnetically active, producing flares and energetic radiation. Over time, such activity may erode atmospheres, especially if a planet lacks strong magnetic protection or sufficient mass. So Proxima Centauri b may be a promising world, or a stripped one, or something in between, we do not yet know. Another widely discussed example is TRAPPIST-1b, and its neighbouring family of planets such as TRAPPIST-1e. These worlds orbit a small cool star in a compact system. Some may retain atmospheres, some may have lost them, and their true conditions remain under active study. Stellar radiation, tidal locking, internal geology, and compositional matter. Thin atmospheres may be common casualties around active stars. This is one reason planetary scientists care so much about stars, not just planets. A planet's sky is partly written by the behaviour of its sun. Why do some worlds lose air? There are several recurring reasons. First, low gravity. Smaller planets struggle to hold lighter gases over long timescales. Molecules move at a range of speeds, and some fast-moving particles in upper atmospheres can eventually escape. Over billions of years, this matters greatly. Second, weak magnetic protection. Charged particles from stellar winds can gradually strip atmospheric particles away, especially when other conditions also favour loss. Third, heat. Warmer atmospheres energise molecules, making escape easier. Worlds close to their stars may lose volatile compounds more readily. Fourth, impacts. Large collisions can remove portions of atmosphere dramatically. Fifth, geology shutting down. If a planet stops replenishing gases through volcanism or other outgassing processes, losses may not be replaced. A breathable atmosphere is not just something you get, it is something a planet must keep. Thin atmospheres also create climate problems beyond breathing. Air transports heat. Dense enough atmospheres move warmth from day to night, pole to equator, sea to land. Remove most of that system, and temperature extremes grow sharper. Deserts freeze at night more easily than humid coastal regions, partly for this reason. Scale that up to planetary levels, and worlds can become thermally unforgiving. Mars again provides an example. Temperatures swing quickly because the thin atmosphere stores relatively little heat. Then there is radiation. Atmospheres shield surfaces from some ultraviolet and energetic particles. A thin atmosphere offers less protection. Combined with weak magnetospheres, surfaces can become harsher places for biology. If you hoped for a pleasant afternoon walk, radiation statistics may intervene. Yet thin atmosphere worlds remain deeply compelling scientifically. Why? Because they preserve stories. Mars preserves ancient river channels, lake beds, sediment layers, and mineral clues to wetter eras. The Moon preserves impact history from early solar system violence. Mercury preserves records of crustal contraction and intense solar interactions. These places are archives. They're inhospitable, but informative, and thin atmospheres may not always be permanent. Terraforming discussions often focus on whether Mars could regain a thicker atmosphere. Could trapped carbon dioxide be released? Could greenhouse warming help? Could imported volatiles build pressure? Current evidence suggests it would be extremely difficult with known accessible resources. Mars may simply lack enough easily mobilized atmosphere-building material to recreate an Earth-like sky on practical timescales. The dream is imaginative. The arithmetic is stern. What would it feel like personally to live under a thin atmosphere, even inside habitats? Every outdoor trip becomes an EVA-style operation. Suits, seals, pressure checks, airlocks, redundancy systems. A torn glove matters. A valve matters. Dust on a gasket matters. You cannot absent-mindedly step outside because you forgot something in the car. There is no just pop out for a minute. Windows become precious because being outdoors is complex. Weather may be visually dramatic but physically unreachable. Smells of open air vanish. Natural breezes vanish. Unfiltered sky contact becomes technical rather than casual. It would change psychology as much as logistics, and this returns us to Earth. Here, pressure is generous enough that lakes remain liquid, weather circulates, sound travels richly, and lungs function with no ceremony. You can open a door and walk into the atmosphere as though it owes you convenience. That is astonishing. We complain about humidity, pollen, wind, or rain, yet all of those complaints happen inside a vast success story. Thin atmosphere worlds teach appreciation through contrast. They show that air is not merely something present or absent. It must be thick enough to work, stable enough to remain, protective enough to matter, and chemically suitable enough to trust. A sky can look beautiful and still be unusable. A horizon can inspire awe and still refuse your next breath. Sometimes the universe offers plenty of atmosphere. It simply offers the wrong kind. After exploring worlds with too little air, we now arrive at a different category of planetary disappointment. Skies that are thick, dramatic, and undeniably present, yet dangerous in ways both immediate and creative. These are places where you would not suffocate because nothing surrounds you. You would suffer because something very much does. A toxic sky can be hot enough to cook, cold enough to shatter comfort, acidic enough to corrode, chemically hostile enough to poison, or dynamically violent enough to make breathing the least of your concerns. It may glow beautifully from afar. It may even resemble the romantic image of a planet with weather and clouds and winds and sunsets. Then you check the details. This is a recurring lesson in planetary science. Beauty is not safety. Clouds are not kindness. Thick atmosphere does not equal hospitality. The cosmos has excellent presentation and inconsistent customer care. Let us begin with perhaps the most famous cautionary tale in our solar system, Venus. From Earth, Venus appears bright and elegant, often the most brilliant object in the sky after the Sun and Moon. It has inspired myths, admiration, and many optimistic assumptions. Yet Venus at the surface is one of the harshest places in the solar system. Its atmosphere is composed mostly of carbon dioxide with clouds containing sulfuric acid droplets. Surface pressure is about 90 times that of Earth's sea level pressure, comparable to conditions deep in Earth's oceans. Temperatures are hot enough to melt lead, caused largely by a runaway greenhouse effect trapping heat under the dense atmosphere. If you landed there unprotected, you would face crushing pressure, extreme heat, and an atmosphere unsuitable for human respiration. The clouds themselves are acidic. The ground is not much of a consolation prize. Venus is what happens when a planet similar in size to Earth takes a very different path. It is a valuable scientific lesson wrapped in a lovely evening star. Now let us travel outward to Titan, one of the most intriguing worlds known. Titan possesses a thick atmosphere, mostly nitrogen, with methane and other hydrocarbons. In some respects, Titan's atmosphere resembles an alternate chemistry version of early Earth more than many planets do. It has weather, clouds, rain, rivers, lakes, and seas. That sounds promising until one small detail arrives. Those lakes are liquid methane and ethane. Titan's surface temperature is around minus 179 degrees Celsius. Water there behaves like rock. Human tissues, equipment, and enthusiasm would all struggle quickly in such cold. There is essentially no breathable oxygen, and the frigid environment changes every practical aspect of survival. Titan's orange haze and active weather make it one of the most fascinating destinations imaginable. It is not, however, ideal for a leisurely outdoor lunch. Next, consider Jupiter. Jupiter does not offer a conventional solid surface, where one might sensibly stand and evaluate local housing options. It is a gas giant composed mainly of hydrogen and helium, with trace compounds such as ammonia, methane, and water deeper within its atmosphere. Descending into Jupiter means entering increasing pressure, increasing temperature, violent winds, and chemistry that grows steadily less accommodating. Its Great Red Spot, a storm larger than Earth that has raged for centuries, is a reminder that weather on Jupiter is a category all its own. If you entered Jupiter's atmosphere, there would be no breathable oxygen, no stable surface, and no gradual friendly zone where matters become reasonable. Conditions would intensify until equipment failed and matter itself reconsidered its life choices. Jupiter is magnificent. It is also not accepting settlers. Let us stay with dangerous chemistry and move to another giant, Neptune. Neptune's atmosphere consists mostly of hydrogen, helium, and methane. The methane helps give the planet its rich blue colour. Again, lovely appearance, difficult reality. Neptune is intensely cold in upper layers and hosts some of the fastest winds measured in the solar system, reaching supersonic speeds in certain regions. There is no breathable air, no solid welcoming surface in the ordinary sense, and no stable mild zone waiting for visitors with scarves. Pressure increases dramatically deeper down, while temperatures and compositions shift through layers still being studied. If Earth weather can ruin plans, Neptune weather can ruin definitions. Now let us move beyond the solar system to one of the most famous exoplanets ever discovered, HD 189733b. This hot Jupiter orbits close to its star and has become well known because observations suggest extreme conditions, including high temperatures and likely silicate particles in the atmosphere. Popular descriptions often mention sideways glass rain driven by fierce winds. While such headlines simplify complex models, the essential truth remains clear: this is not a breathable paradise. Imagine a world where winds scream at thousands of kilometers per hour and hot mineral particles may move through the atmosphere. Even by cosmic standards, that feels unfriendly. Then there is WASP-76b, another celebrity among inhospitable worlds. WASP-76b is so hot on its day side that some metals can vaporize. Studies suggest iron may condense and fall on the cooler night side, leading to the widely shared phrase iron rain. As always, the real science is nuanced, but the broad point is solid. Temperatures are extreme enough for chemistry humans do not generally include in vacation planning. No oxygen-rich breeze, no meadow, lightly metal weather. Astronomy can be wonderfully direct at times. Another famous case is 55 Cancri E. This rocky exoplanet orbits very close to its star and experiences extreme heating. Surface temperatures are believed to be high enough to melt rock in some regions. Depending on models and observations, it may possess a thin atmosphere or transient envelope, shaped by intense irradiation and volcanic processes. Whatever the exact details, breathable suburban calm is not among them. These examples show an important truth. Having an atmosphere is easy compared with having the right atmosphere. Why do so many worlds become toxic or hostile? There are several recurring pathways. First, greenhouse trapping. If a planet accumulates enough heat-trapping gases, especially close to its star, temperatures can rise dramatically. Water may evaporate, adding further greenhouse warming. Feedback loops can push conditions into runaway states. Venus is the classic example. Second, stellar proximity. Many exoplanets orbit very close to their stars because such planets are easier to detect. Close orbits often mean tidal locking, intense radiation, atmospheric stripping, extreme temperature contrasts, or overheated atmospheres. Third, composition from birth. Planets form from disks of gas and dust with different materials available at different distances from their stars. Some become hydrogen-rich giants. Others retain volatile compounds like methane or ammonia. Not every world begins with Earth-like ingredients. Fourth, mass and gravity. Large planets can retain thick primordial atmospheres. Small planets may lose theirs. Both extremes can frustrate human breathing for opposite reasons. Fifth, geology and chemistry over time. Volcanism, ocean loss, impacts and interactions with sunlight reshape atmospheres across billions of years. In short, skies evolve, sometimes toward comfort, often elsewhere. There is another subtle point worth considering. Toxic for humans does not necessarily mean lifeless. A methane-rich cold moon or acidic cloud layer may still host interesting chemistry. Microbial possibilities on certain worlds remain open scientific questions. Our standards are human-centered because our lungs are involved, but the universe may host forms of life with very different tolerances. That should encourage humility. We are not the universal measure of habitability. We are simply one demanding species with fragile air preferences. Still, from a settlement perspective, toxic skies create enormous barriers. Colonists on such worlds would need sealed habitats, filtered atmospheres, pressure management, radiation protection, industrial systems, agriculture support, and endless maintenance. Every door becomes an airlock. Every outdoor task becomes a procedure. Every leak becomes urgent. The romance of living on another planet quickly becomes maintaining a life support infrastructure with no margin for laziness. This does not make exploration pointless. It makes it honest. Titan might host extraordinary science and perhaps one day robotic industry. Venus's clouds may contain altitudes more temperate than its surface, inspiring floating habitat concepts. Gas giant moons could be more practical than the giants themselves. Toxic worlds can still teach us, supply resources, or host specialized stations, but breathing freely beneath open skies is another category entirely. That distinction matters because people often ask whether we can live somewhere when they really mean something more specific. Can we walk outside there? Can children play there? Can crops grow in natural soil beneath natural weather? Can a person wake, open a window, and trust the air? On Venus, no. On Jupiter, no meaningful window exists for that question. On Titan, no without extraordinary protection. On HD 189733b, no, unless one enjoys speculative glass storms. On WASP 76b, no, unless one has solved metal rain etiquette. On many known worlds, the answer remains stubbornly no, which brings us back once again to Earth. Here, clouds are mostly water. Rain does not usually dissolve equipment. Winds can be troublesome, but they rarely reach hot Jupiter absurdity. Temperatures vary, yet much of the planet remains biologically generous. Our atmosphere contains abundant nitrogen, usable oxygen, manageable pressure, and chemistry that supports forests, birds, oceans, and your ability to yawn indoors without a permit. We call this normal because we were born into it. A better word might be exceptional. Toxic skies also sharpen our understanding of what astronomers mean when they search for habitable zones. Not too hot, not too cold is only the beginning. A planet may orbit at a temperate distance and still wear a deadly atmosphere. Surface pressure may be wrong. Chemistry may be wrong. Water may be absent. Clouds may hide disaster. Habitability is not one number from a star. It is a long negotiation between light, rock, gas, time, and luck. When people imagine whether a planet might be livable, they often picture the planet first. They think of oceans, mountains, clouds, deserts, forests, gravity, perhaps dramatic rings for aesthetic value. They imagine standing on the surface, looking outward. That makes sense. We are surface creatures. We think in landscapes. But from the perspective of planetary survival, the more important character may be overhead. The star. A planet's atmosphere is not an independent possession. It is part of an ongoing relationship with the star it orbits. The star provides light, heat, radiation, particle winds, and long-term change. It can help an atmosphere persist, reshape it slowly, strip it away, freeze it out, overheat it, or drive chemistry so strange that the sky becomes something entirely different from what the planet began with. In many ways, a planet's air is the biography of its star written in gas. This means that when we ask whether there are other planets we can breathe on, we're also asking which stars are gentle enough, stable enough, and patient enough to allow breathable atmospheres to exist. That narrows the field more than many people realize. Let us begin with our own star, Sun. The Sun is not perfectly calm. It produces solar flares, sunspots, coronal mass ejections, changing magnetic cycles, and occasional energetic tantrums. Yet compared with many stars, especially in the context of long-term habitability, it has been remarkably serviceable. It is stable enough to provide billions of years of fairly consistent energy output, giving Earth time to develop oceans, complex chemistry, microbial life, forests, mammals, and eventually people who misplace charges. That kind of long stability matters immensely. Life, especially complex life, appears to require time. Microbes may emerge relatively quickly under the right conditions, but breathable atmospheres shaped by biology and ecosystems capable of sustaining complexity can take vast stretches of planetary history. A wildly erratic star may not grant that time. Stars come in many types. Some are larger, hotter, and brighter than the Sun. Some are smaller, cooler, dimmer, and far more numerous. Each category creates different atmospheric challenges for surrounding planets. Let us talk first about red dwarfs, also known as M-dwarf stars. These small cool stars are the most common stars in our galaxy. That alone makes them exciting. If most stars are red dwarfs, then many planets orbit red dwarfs. If many planets orbit red dwarfs, then statistically some may seem promising. Indeed, several of the most famous nearby exoplanets orbit such stars, including Proxima Centauri b around Proxima Centauri, and multiple planets in the TRAPPIST-1 system such as TRAPPIST-1e. This sounds encouraging. Then the complications arrive. Red dwarfs often have active youth phases that can last a very long time. They may produce intense flares, ultraviolet radiation bursts, and stellar winds capable of battering nearby planets. Because red dwarfs are dimmer than the Sun, planets must orbit closer in order to receive temperate levels of warmth. Closer orbit means stronger exposure. That combination can be harsh on atmospheres. Energetic radiation can split molecules. Stellar wind particles can erode upper atmospheric layers. Water molecules may be broken apart, with lightweight hydrogen escaping to space. Over long timescales, a once promising planet could become dry, stripped, or chemically transformed. So a planet in the habitable zone of a red dwarf may be warm enough for liquid water in principle, while simultaneously being blasted by the sort of weather forecast no lungs appreciate. This does not rule such worlds out. Some planets may retain thick atmospheres, magnetic fields, oceans, or geological renewal systems that help them endure. But it means the star must be considered as seriously as the planet. Then there is tidal locking. Planets orbiting close to small stars may become tidally locked, showing one side permanently to the star while the other remains in eternal night, much as the moon keeps one face toward Earth. If a world lacks enough atmosphere or ocean circulation, the day side may overheat while the night side freezes. A substantial atmosphere, however, could transport heat around the globe and soften those extremes. Again, the atmosphere's fate depends on the star, and the climate's fate depends on the atmosphere. Everything is negotiating with everything else. Now consider larger, hotter stars such as A-type stars. These stars burn brighter and hotter than the Sun. A habitable zone planet would orbit farther out. Yet many of these stars live shorter lives on the main sequence. Some may not remain stable long enough for complex life to evolve through slow biological steps. If a star burns through its calm adulthood quickly, a planet may receive suitable temperatures but insufficient time. It is a bit like renting a beautiful apartment that will be demolished next Thursday. There may be time to admire the kitchen, but perhaps not to build civilization. Stars somewhat like the Sun, especially G-type stars and many K-type stars, often receive attention as favourable hosts. K-dwarfs, slightly smaller and cooler than the Sun, are particularly interesting. They may live longer than G-type stars while being less violently active than many red dwarfs. Some researchers have even suggested that certain K-dwarfs could be especially promising for habitability. The universe naturally has not yet confirmed reservations. Stars also change with age. The Sun itself has grown brighter over geological time. Early Earth received less solar energy than today, a puzzle known partly through what is sometimes called the faint young sun paradox. Despite a dimmer young sun, Earth maintained liquid water. Greenhouse gases likely helped compensate. This teaches an important lesson. Habitability is not static. A planet may be too cold early on, comfortable later, and too hot much later. Atmospheres evolve in response. Ice may melt, oceans may evaporate, carbon cycles may stabilize or fail. Worlds pass through windows of opportunity. Some windows last billions of years, some may be brief. Even our own future is tied to stellar change. The Sun will continue brightening gradually. Over immense timescales, Earth may become less hospitable long before the Sun becomes a red giant. Increased heating could intensify weathering, reduce carbon dioxide available for plants, alter oceans, and eventually destabilize surface habitability. The star that enabled our biosphere will one day outgrow the arrangement. No offense intended. It is simply stellar aging. Stars also determine atmospheric chemistry through their light spectrum. Different stars emit different proportions of ultraviolet, visible, and infrared radiation. That matters because certain wavelengths drive photochemistry. Ultraviolet light can split molecules like water, methane, and carbon dioxide. Ozone formation and destruction depend strongly on UV conditions. Haze layers may form in some atmospheres under particular stellar illumination. Thus, the same planet orbiting two different stars might develop very different skies. One may become clear, one hazy, one oxygen-rich, one stripped, one temperate, one ruined. Same rock, different parent. This should make us cautious when reading headlines about Earth-size planet discovered. Size alone tells little. Orbital distance helps, but still not enough. Star type, age, activity, spectrum, magnetic behavior, and history all matter. A breathable world is not merely built from stone. It is raised by sunlight. Let us return briefly to real examples. Kepler 452b became famous as an Earth cousin candidate because of its size and orbit around a Sun-like star. Yet many details remain uncertain. Is it rocky? How thick is its atmosphere? What is its geologic state? Has increased stellar brightness over time pushed it toward a greenhouse future? We do not know enough yet. Another notable case is Kepler 186f, one of the first Earth-sized planets found in the habitable zone of another star, specifically a red dwarf. Exciting, certainly. But again, stellar environment raises questions about atmospheric retention and long-term surface conditions. Discovery is often the first sentence, not the last. Stars also influence planetary spin and orbit stability. Gravitational interactions in multi-planet systems can alter eccentricity, changing seasons or causing climate swings. Some planets experience tidal heating from gravitational flexing, as seen dramatically in moons like Io, where volcanism is extreme. On exoplanets, tidal heating might help subsurface oceans, or create excessive instability depending on circumstances. Once again, stars are not just lamps, they are architects. There is a comforting implication hidden inside all this complexity. Breathable atmospheres may require many favourable conditions, yes, but stars are abundant. The Milky Way contains hundreds of billions of them. Even if only a fraction are suitable hosts, and only a fraction of those host rocky planets, and only a fraction of those retain kind atmospheres, the remaining number could still be substantial. Statistics can be generous even when standards are strict. Still, for any individual world, the star is often judge, sponsor, and hazard combined. If it is too violent, atmospheres may erode. Too bright, oceans may vanish. Too dim, surfaces may freeze unless greenhouse warming compensates. Too short-lived, biology may run out of time. Too variable, climate may become unstable. Just right, and a sky may learn patience. That phrase may sound sentimental, but atmospheres are records of endurance. Billions of years of balance between incoming energy, outgoing heat, chemistry, geology, and perhaps life itself. Earth's atmosphere exists because the Sun has been stable enough, and because Earth has responded skillfully enough for a very long time. Not perfectly, but successfully. There is another reason this topic matters. If humanity ever settles other systems, choosing a destination means choosing a star. Colonists would not only ask about planets, they would ask whether the host star flares often, whether radiation levels are manageable, whether orbital conditions are stable, whether future climate windows remain open for millions of years. Real estate becomes astrophysics quickly. One can imagine future advertisements. Temperate moon, scenic ocean views, low flare frequency, mature K-dwarf neighbourhood, excellent long-term prospects. Applications pending. For now, our telescopes continue gathering clues. Instruments analyse transits, stellar spectra, planetary masses, atmospheric signatures, and flare behaviour. With each improvement, we move from counting planets to characterising worlds. And every characterization begins with a star. Because before a planet can offer breathable air, it must survive the thing that lights its sky. There may be no phrase in popular astronomy more charmingly optimistic than the habitable zone. It sounds so tidy, so reassuring, as though every star wears a neat golden ring around it, where pleasant weather, flowing water, breathable air, and reasonable property values naturally appear. One imagines a cosmic estate agent pointing helpfully at a diagram. Here we are, ideal orbit, southern exposure, potential for oceans. If only it were that simple. The habitable zone is a real and useful scientific concept, but it is often misunderstood. It does not mean a planet is habitable. It does not guarantee breathable skies, forests, beaches, or even a surface worth standing on. It simply describes a range of distances from a star where temperatures might allow liquid water to exist on a rocky planet's surface, assuming suitable atmospheric conditions. That last part does a great deal of work. In plain language, the habitable zone is about incoming stellar energy. Too close to the star, and a planet may become so warm that water evaporates, greenhouse heating intensifies, and oceans may eventually be lost. Too far away, and water freezes extensively, potentially locking the surface beneath ice. Between those extremes lies a region where liquid water could be possible. Could. Science often hides caution inside small words. Water matters because all known life depends on it, and because liquid water supports chemistry, climate regulation, transport of nutrients, erosion, weathering, and many processes associated with planetary stability. If you are searching for life as we know it, liquid water is an excellent clue. But water alone is not enough. You can place a planet in the habitable zone and still end up with something deeply inconvenient. Let us begin with our own solar system, because it provides excellent examples of why the habitable zone is not a magical guarantee. Earth sits comfortably within the Sun's habitable zone and, to no one's surprise, contains abundant liquid water. This has encouraged centuries of optimism. Now look next door at Venus. Venus lies near the inner edge of the Sun's habitable region depending on model definitions. It is similar in size to Earth, yet today Venus is a furnace beneath a dense carbon dioxide atmosphere with crushing pressure and sulfuric acid clouds. Surface temperatures are hot enough to melt lead. If you judged only by distance from the Sun, Venus might have seemed promising. Reality filed an objection. Then look outward to Mars. Mars lies near or beyond the outer edge depending on model details and epoch. It once had rivers, lakes, and a thicker atmosphere. Today it is cold, dry, and wrapped in thin air. Liquid water is unstable on the surface under many present conditions. Mars may once have been more habitable than now. Same star, same broad zone, different outcomes. Already we see the problem. Orbital distance matters, but it is only the beginning. Atmosphere is the next major factor. A planet's atmosphere determines how much heat is trapped, reflected, redistributed, and lost. Carbon dioxide, water vapor, methane, clouds, aerosols, and pressure all influence surface temperature. A world receiving Earth-like sunlight could be frozen under the wrong atmosphere or scorching under the wrong one. Think of the habitable zone as room temperature guidance for a house whose windows, insulation, roof, and furnace remain unknown. Not useless, but incomplete. Clouds complicate matters further. Bright reflective clouds can cool a planet by sending sunlight back to space. High-thin clouds may warm by trapping infrared heat. Cloud behavior depends on rotation, oceans, topography, atmospheric circulation, aerosols, and chemistry. A planet with oceans and active weather may regulate itself differently from a dry, rocky world. Now let us leave the solar system. Thousands of exoplanets have been discovered, and many headlines celebrate planets in the habitable zone. This is often justified excitement, but interpretation requires restraint. Consider Kepler 186f. This was one of the first Earth-sized planets found in the habitable zone of another star, a red dwarf. Important discovery, genuinely historic. But does it have an atmosphere? What composition? How thick? Is it tidally locked? How active is the star? Is there water? Unknown, 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 and more unknown. Still valuable, just not solved. Then there is Proxima Centauri b, orbiting the nearest star to the Sun. It lies in a region where temperatures could allow liquid water under some conditions. Wonderful news, except its star, Proxima Centauri, is a flare-active red dwarf. Radiation and stellar winds may challenge atmospheric survival. If the atmosphere has been stripped, the habitable zone matters much less. A perfect address with no roof remains problematic. Another famous system is TRAPPIST-1, with several Earth-sized planets, including TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, often discussed as temperate candidates. This system fascinates astronomers because multiple rocky worlds orbit one nearby small star. Yet again, questions remain about atmospheres, water inventories, stellar activity, and long-term climate states. The habitable zone gives targets. It does not give conclusions. There is another issue many people overlook. Habitability can change over time. Stars brighten gradually as they age. Our own sun is brighter now than in Earth's distant past. A planet may begin too cold, enter a long favourable era, then eventually become too hot. Some worlds may spend billions of years in a useful zone. Others may cross through it briefly. This means a planet could be in the habitable zone now but sterile due to earlier atmospheric loss. Or it could be currently frozen, waiting for future warming. Timing matters almost as much as location. Geology matters too. A planet with active volcanism may replenish atmospheric gases. Plate tectonics may help regulate carbon over long timescales. Interior heat may sustain oceans beneath ice. Magnetic fields may help shield atmospheres from stellar particles. Two planets with identical size and sunlight can diverge dramatically if one has active geology and one is geologically spent. Life itself may alter the zone. On Earth, biology changed atmospheric oxygen levels and influences carbon cycling. Forests, plankton, soils and microbial communities help shape climate and chemistry. If life emerges elsewhere, it may modify planetary conditions, perhaps extending or stabilizing habitability. This is a profound twist. We search for habitable planets as though habitability precedes life. Sometimes life may become part of what makes a planet habitable. The term Goldilocks zone is often used in popular writing, not too hot, not too cold, just right. It is catchy and broadly useful for introducing the concept. But even Goldilocks would need more information. What is the pressure? What is the atmosphere made of? Are there oceans? How violent is the star? How long has the climate been stable? Is there radiation shielding? Does water exist as lakes, steam, buried ice, or not at all? Can chemistry support complex life? Can lungs do anything useful there? Goldilocks was selective. She would ask follow-up questions. There are also habitable possibilities beyond the classic surface water zone. Some moons or planets outside standard habitable regions may host subsurface oceans warmed by tidal heating or internal radioactivity. Europa and Enceladus are famous examples in our solar system. Their surfaces are frozen, but beneath the ice may lie liquid oceans. These are exciting targets for life searches. They are not breathable outdoor worlds for humans. Again, habitable for life is not the same as habitable for us. This distinction is crucial. Microbes may thrive in places where humans would perish instantly. We often ask whether a planet is habitable when we really mean whether unprotected human life could comfortably exist there. That standard is much narrower. If our topic is planets we can breathe on, then the habitable zone becomes even less sufficient. Surface liquid water may be possible while the atmosphere remains toxic, thin, crushing, oxygen-free, or otherwise rude. A world with oceans of water and skies of carbon dioxide still fails the lung test. Another subtle complication is rotation and climate circulation. Slowly rotating or tidally locked planets may develop thick cloud decks over the star-facing side, reflecting light and cooling the surface more than expected. Fast rotators may distribute heat differently. Continents and oceans influence winds and heat storage. Climate models for exoplanets are improving constantly, because the simple ring around a star keeps proving too simple. That is how science progresses. We keep replacing cartoons with details. Still, the habitable zone remains valuable. It helps prioritize searches. Telescopes have limited time. Scientists need places to look first. If a rocky planet receives roughly suitable energy from a stable star, it becomes interesting. Not confirmed paradise. Interesting. And interesting is enough to justify careful attention. There is also something emotionally appealing about the concept. It suggests that life is not impossible luxury, but something nature can support under understandable conditions. Warmth, water, chemistry, time. We may not be alone because the recipe itself is not absurdly specific, yet every added detail reminds us that success likely requires many ingredients interacting over ages. That does not reduce hope. It refines it. Perhaps breathable worlds are not everywhere, but neither are they impossible. They may be rare gardens rather than common weeds. Rare still leaves room for many in a galaxy this large. Meanwhile, Earth continues to demonstrate what a fully successful case looks like. Right distance from a stable star, long-lived oceans, moderated climate, active geology, protective magnetic field, life-reshaping atmosphere, and billions of years of continuity. The habitable zone placed Earth in contention. Everything else helped it win. That perspective can deepen gratitude. We often speak of Earth as though it merely happened to be comfortable. In truth, comfort here is the visible result of countless hidden systems cooperating across deep time. A lucky orbit was only the invitation. The rest was built. When people dream about living beyond Earth, the imagination usually travels somewhere nearby before it travels far. That is understandable. The nearest worlds feel more tangible. They have names we learned young. We can see some of them with our own eyes. Spacecraft have photographed their deserts, clouds, craters, volcanoes, valleys, and storms. They are not abstract dots around distant stars. They are neighbours. And among those neighbours, two planets dominate the conversation whenever human expansion is discussed: Mars and Venus. Mars is the practical fantasy. Venus is the cautionary mystery. Both are rocky worlds. Both are relatively close by cosmic standards. Both likely had histories more complex and dynamic than their current surfaces first suggest. Both may once have been more hospitable than they are now, and neither allows you to step outside and breathe. Not yet. Let us begin with Mars, because Mars has become the favoured destination of future-minded engineers, scientists, science fiction writers, and anyone who has ever looked at a red horizon and thought, perhaps. Mars appeals to us for several reasons. Its day length is similar to Earth's, just over 24 hours. It has seasons due to axial tilt. Water exists there as ice, and perhaps brines or hidden reserves in some forms. Its gravity, while weaker than Earth's, is substantial enough to feel more planet-like than microgravity. Temperatures, though often bitterly cold, can sometimes rise above freezing in certain locations and times. Most importantly, Mars has a surface one can imagine using. It has plains, mountains, canyons, polar caps, dust and geology that feels like a place rather than a giant pressure chamber. Yet the atmosphere changes everything. Mars has a thin atmosphere, mostly carbon dioxide, with surface pressure averaging less than 1% of Earth's sea level pressure. That means no breathable oxygen, no sufficient pressure for unprotected human lungs, and severe challenges for liquid water stability. Step outside without a suit, and survival time would be measured badly. Even if Mars had Earth-like oxygen percentages, the pressure would still be far too low for normal breathing. Pressure, as we have learned, is not optional. Mars is also cold. Average temperatures are well below freezing, though they vary significantly by location and season. Dust storms can cover enormous regions. Radiation exposure is higher because Mars lacks a thick atmosphere and global magnetic field comparable to Earth's, so Mars offers land but not hospitality. Still, Mars remains attractive because many of its problems look engineering-shaped. Habitats can be pressurized, water ice can be mined, carbon dioxide can be processed, local resources may support fuel production, construction materials, and agriculture in controlled environments. Mars does not currently welcome humans, but it may permit determined guests. That distinction matters. We have already sent robotic emissaries there in abundance. Curiosity and Perseverance roam its surface, studying rocks, climate, and ancient environments. Orbiters map minerals and weather. Helicopter technology was demonstrated by ingenuity in air so thin it barely deserves the term by Earth standards. Mars continues to teach us that dead-looking worlds may have active stories. Its dried river valleys, delta deposits, and sediment layers suggest a wetter past. Long ago, Mars likely had thicker air and surface water. Something was lost. That loss is one reason Mars fascinates us emotionally. It may be a world that once came closer to comfort than it does now. Now let us turn inward to Venus. Venus is often called Earth's twin because of its similar size and rocky composition. But twins can grow apart dramatically. Today, Venus is wrapped in a dense carbon dioxide atmosphere with clouds of sulfuric acid. Surface pressure is around 90 times Earth's sea level pressure. Temperatures are hot enough to melt lead. Winds high in the atmosphere move swiftly, while the surface remains a place where landers survive only briefly unless heavily engineered. If Mars is too little atmosphere, Venus is too much of the wrong atmosphere. It is tempting to think of Venus as permanently hopeless, but Venus is scientifically richer than that. Many researchers suspect Venus may once have had liquid water and more temperate conditions long ago. If true, then Earth and Venus began with more similar possibilities before diverging dramatically. Why did one world become blue oceans and forests, while the other became a runaway greenhouse furnace? That is one of the great comparative questions in planetary science. Venus reminds us that being in or near a habitable zone is not enough. Planetary climate can tip. Water can be lost. Feedback loops can accelerate warming. Atmospheres can become traps. It is less a failed Earth than a warning that worlds are dynamic. And yet Venus has one strange advantage over Mars. At certain altitudes high in the Venusian atmosphere, temperatures and pressures become far more moderate than at the surface. This has inspired ideas for floating habitats or research stations suspended in the clouds. The chemistry remains difficult and corrosive, but in some respects the skies of Venus are more physically tolerable than the ground. A planet where the clouds are friendlier than the surface is wonderfully inconvenient. Would humans ever live there? Perhaps as stations rather than open-air settlements. Balloons, aerostats, floating laboratories, industrial platforms. It is speculative, but not absurd. No one would be opening windows casually. Beyond Mars and Venus, we should mention other nearby neighbours often imagined in broader colonization dreams. Moon is not a planet, but it remains our nearest major destination. It has essentially no breathable atmosphere. Habitats would be fully artificial. Dust is abrasive. Radiation protection matters. Temperature swings are severe. Yet the Moon's proximity makes it a likely long-term base for industry, science and training. The Moon is not breathable. It is practical. Then there is Titan, Saturn's moon with a thick nitrogen atmosphere and methane weather. Too cold to breathe, no oxygen, but pressure at the surface is closer to useful than Mars. In a strange twist, Titan's pressure is more comfortable than its chemistry or temperature. Sometimes a world solves the wrong problem. Europa likely hides a global ocean beneath ice. Scientifically thrilling. Breathable? Not remotely in open conditions. This pattern repeats often. Interesting worlds are common. Easy worlds are not. Could Mars be terraformed into something breathable? The idea is famous. Warm the planet, thicken the atmosphere, release carbon dioxide from ice caps and soil, import volatiles, introduce engineered biology over long timescales. It is imaginative and may one day inspire serious attempts. But current estimates suggest Mars likely lacks enough easily accessible carbon dioxide to create Earth-like pressure with presently known resources. Terraforming Mars may be vastly harder than many casual summaries imply. The dream survives. Physics remains reserved. Could Venus be terraformed? That challenge may be even larger. One would need to cool the planet dramatically, remove or transform enormous amounts of atmospheric carbon dioxide, manage pressure, and perhaps restore water inventories. It is difficult enough that most discussions drift quickly from engineering into epic mythology. Venus asks for civilization-scale effort before lunch. This raises an important question. If neither Mars nor Venus is naturally breathable, why are they discussed so much? Because proximity matters, distance is expensive, communication delay matters, rescue options matter, transport windows matter. If humanity expands beyond Earth, nearby difficult worlds may be more realistic than distant perfect worlds. An unpleasant neighbour can be easier than a lovely stranger 40 light-years away. That is true in real estate and astrophysics alike. There is also psychological value in nearby worlds. Mars gives us a frontier with visible ground. Venus gives us a climate lesson with terrifying clarity. The Moon gives us a test bed. These places are classrooms as much as destinations. They force us to learn closed-loop life support, radiation shielding, habitat design, autonomous industry, food systems, medicine in partial gravity, and the social challenge of living where a broken valve matters more than most politics. Before we can breathe elsewhere, we may need to master surviving where we cannot. Another subtle truth emerges here. Humans often imagine colonization as replacing Earth. Mars instead looks more like an extension of Earth's infrastructure. Settlers would depend on technology, supply chains, maintenance, medicine, software, spare parts, and continuous competence. The first Martian city, if it comes, will owe much to engineers who hate leaks. Venus cloud habitats, lunar bases, asteroid stations, and Martian domes would all share this principle. We bring our atmosphere with us. That is a very different thing from finding a world that provides it freely. And perhaps that is why truly breathable planets remain such powerful symbols. A habitat is impressive, a dome is practical, a sealed colony is admirable, but a place where a child could run outdoors under open sky without equipment, that feels like home. Mars and Venus are not there yet. Mars is too thin, too cold, too exposed. Venus is too hot, too dense, too chemically harsh. They may host future outposts, industries, laboratories, maybe even cities under shells or within clouds. But neither currently offers the simplest luxury Earth provides every moment. Step outside, inhale, continue. That ordinary ease remains rare enough that our nearest planet still cannot match it. Not every promising world wears its habitability on the outside. Some planets and moons seem, at first glance, entirely discouraging. Frozen crusts, bitter cold, no breathable atmosphere, little sunlight, surfaces that appear silent, barren, and far too far away to inspire comfortable real estate fantasies. If judged only by what stands on top, many of these places would be dismissed quickly. But planetary science has developed a healthy suspicion of surfaces. Again and again, worlds that look dead above may be active below. Ice can hide oceans. Rock can hide heat. Darkness can hide chemistry. A frozen shell may cover liquid water deeper down, warmed not by sunlight but by tidal forces, radioactive decay, or residual internal heat. And if liquid water exists, scientists pay attention. This brings us to some of the most fascinating places in the search for life. Ocean worlds and ice moons. These are bodies where water may exist in large amounts beneath frozen exteriors, sometimes in global oceans deeper than anything on Earth. They may not offer open skies we can breathe, but they challenge a simple assumption that habitable means warm surface with blue weather. The universe may prefer secrecy. Let us begin with one of the great stars of planetary intrigue, Europa. Europa is slightly smaller than Earth's moon, and wrapped in a bright shell of water ice crossed by dark fractures and ridges. Beneath that frozen crust, evidence strongly suggests a vast, salty liquid ocean. This ocean may contain more water than all of Earth's oceans combined. That is a startling sentence, and yet it may be true. Europa is heated partly by tidal flexing. As Jupiter's immense gravity pulls and releases Europa during its orbit, the Moon's interior bends slightly, generating heat through friction. This process helps prevent the hidden ocean from freezing solid. Imagine a world where tides are not merely beach schedules, but planetary life support. Why does Europa matter so much? Because where there is liquid water, rock contact, chemistry and energy, there may be conditions suitable for life. On Earth, deep ocean hydrothermal vents teem with ecosystems independent of sunlight. If something similar exists on Europa's seafloor, biology becomes a serious question. Could humans breathe there? No open-air answer exists because there is no friendly open air. Europa's surface is exposed to intense radiation from Jupiter's magnetosphere. Temperatures are brutally cold, and the atmosphere is extremely tenuous. Any human presence would require shielded habitats and substantial engineering. Still, beneath the ice may lie one of the most promising oceans in the solar system. Now, let us travel to Enceladus. Enceladus is much smaller than Europa, yet it has become one of the most beloved objects in planetary science. Why? Because it sprays evidence into space. From fractures near its south pole, Enceladus emits plumes of water vapour, ice particles, salts, and organic compounds. NASA's Cassini flew through these plumes and found clues consistent with a subsurface ocean interacting with a rocky core. This is scientific generosity of the highest order. Rather than forcing us to drill through kilometres of ice immediately, Enceladus throws samples upward for inspection. The hidden ocean may contain hydrothermal activity, which means chemical gradients and heat sources potentially useful for life. If microbes exist there, Enceladus might one day help us detect them more easily than worlds that keep their secrets entirely buried. Breathable skies, however, remain absent. Enceladus has no human-friendly atmosphere, and surface temperatures are deeply inhospitable. A marvellous laboratory, a poor picnic site. Next comes the giant and elegant Titan. Titan is unique. It has a thick atmosphere, mostly nitrogen, thicker than Earth's in surface pressure terms, with methane clouds, methane rain, rivers, lakes, and seas of liquid hydrocarbons. It is one of the few places beyond Earth with stable liquids on the surface. The catch, naturally, is temperature. Titan is so cold that water ice behaves like rock, while methane takes on roles water fills here. Yet beneath Titan's icy crust, many models indicate a subsurface ocean of liquid water mixed with other compounds. So Titan may host two very different worlds at once, a hydrocarbon weather system above and a hidden water ocean below. That is almost excessive creativity from one moon. Could humans breathe on Titan? No, there is no free oxygen and the cold would rapidly end casual optimism. But Titan's thick atmosphere does offer shielding and aerodynamic advantages. In theory, flying there would be strangely easy because dense air and low gravity are cooperative. You still should not remove the helmet. Now consider Ganymede. Ganymede is the largest moon in the solar system, bigger than the planet Mercury. It likely contains multiple layers of ice and liquid water beneath its surface. Some models suggest a complex stack of oceans separated by high-pressure ice layers. Ganymede is also notable for possessing its own magnetic field, rare among moons. That magnetic field does not make it cozy, but it does make it scientifically interesting. Its surface is cold and the atmosphere is extremely thin, containing traces such as oxygen in tenuous form, nowhere near breathable conditions. Yet inside, water and internal structure hint at long-term complexity. A moon larger than planets with hidden oceans is exactly the sort of fact astronomy enjoys offering casually. Then there is Callisto, often overshadowed by Europa and Ganymede. Callisto may also harbour a subsurface ocean beneath ancient cratered terrain. It is heavily battered by impacts and geologically quieter than Europa, but still significant. Some future mission planners have considered Callisto attractive for human operations in the Jovian system, because it lies farther from Jupiter's most intense radiation belts than Europa. Translation: still difficult, but slightly less aggressively so. No breathable atmosphere exists there either, but location matters when every environment is challenging. Let us widen the view. Ocean worlds need not be moons only. Distant dwarf planets and large icy bodies may also hide internal seas. Pluto shows evidence of surprising geological complexity, and may have retained a subsurface ocean for long periods, or perhaps still today depending on internal models. Ceres contains water-rich materials and signs of briny activity. The solar system appears less like a dry museum, and more like a place where water keeps turning up behind locked doors. Why does this matter for our larger question about breathable worlds? Because it reminds us that life and human comfort are separate categories. An ocean world beneath ice may be excellent for microbes and terrible for tourists. A moon with chemical energy and stable water may host biology while offering no open sky, no forests, no breathable breeze, no sunlight worth speaking of. We must be careful with the word habitable. For bacteria, a warm crack in rock may suffice. For humans, standards rise sharply. We ask for pressure, oxygen, moderate temperatures, radiation shielding, food systems, gravity tolerance, psychology support, and somewhere to complain about the weather. Still, these worlds matter enormously because discovering even simple life elsewhere would transform our understanding of biology. If microbes arose independently in Europa's ocean or Enceladus's vents, then life may emerge wherever conditions allow. That would make the universe feel both more crowded and more interesting. It would also suggest breathable worlds may not be the only prize. There is another intriguing phrase in your topic title. Can we breathe on other planets? Ocean worlds suggest a twist. Perhaps we cannot breathe there naturally, but perhaps we could build places there. Imagine subsurface habitats melted into European ice, shielded from radiation by kilometers of frozen water overhead. Imagine floating laboratories in Titan skies. Imagine enclosed cities near resource-rich plumes of Enceladus. Imagine stations on Callisto supporting exploration of the Jovian system. In each case, we bring the air ourselves. That may be how much of human expansion begins, not by finding Earth 2.0, but by carrying Earth in pieces. Life support systems, greenhouses, recycled water, pressure vessels, microbes, seeds, metals, software, stubbornness, portable atmosphere. There is also poetry, though we promise not to overdo that sort of thing, in the fact that some worlds hide oceans from the stars. On Earth, water and sky speak openly. Clouds rise, rain falls, rivers run in daylight. On Europa or Enceladus, the sea may never see the sun, and yet it may still move, circulate, react, perhaps even live. A hidden ocean does not need applause. Would humans psychologically thrive in such environments? That is another matter. Living under ice, under domes, under constant technical dependence, far from open, breathable air, would demand resilience. We evolved under skies, horizons, weather, birds, wind in trees, and sunlight cycles. Replace all that with corridors and machinery, and culture must adapt. Some people would love it. Some would miss rain terribly. That emotional layer often gets ignored in colonization talk. Survival is not the same as flourishing. A sealed base on Europa may be scientifically glorious and personally difficult. Even so, ocean worlds may become some of our most important destinations because they combine accessible scientific mystery with resources. Water means drinking supply, oxygen extraction, hydrogen fuel potential, radiation shielding mass, and industrial usefulness. Frozen inconvenience can become logistical wealth. As telescopes improve, we're also finding exoplanets that may be water-rich or ice-covered on larger scales. Some so-called water worlds could possess global oceans hundreds of kilometers deep. Others may be frozen exteriors with internal seas warmed from below. Their exact conditions remain uncertain, but the theme is clear. Surface appearances mislead. A dry-looking rock may hide ice, a frozen shell may hide ocean, a hostile exterior may hide chemistry patient enough for life. This brings us back to Earth once more. Our world combines what many others divide. We have open liquid oceans, breathable sky, sunlight at the surface, moderate pressure, active climate, accessible land, and biology thriving in plain view. Many worlds may have one or two of these gifts. Earth has a remarkable bundle of them. For a long time, human imagination stocked the galaxy with familiar choices. We pictured planets like Earth, planets like Jupiter, perhaps the occasional Mars-like desert or icy moon for dramatic effect. Our own solar system became the template. Rocky inner worlds, giant outer worlds, a tidy arrangement that seemed, if not universal, then at least respectable. Then exoplanet discoveries began arriving in earnest, and the universe politely informed us that our sample size had been 1. Among the greatest surprises were worlds we do not have in our own planetary family, super-Earths and mini-Neptunes. These planets are now known to be common throughout the galaxy, perhaps among the most common categories of planet around other stars. Yet they have no perfect local equivalent for us to compare directly. That alone makes them fascinating. A super-Earth usually refers to a planet more massive than Earth, but lighter than the ice giants, especially if likely rocky or partly rocky. A mini-Neptune generally refers to a planet smaller than Neptune but larger than Earth, often with a thick atmosphere rich in hydrogen, helium, or volatile compounds. The names can be misleading. A super-Earth is not automatically Earth, but better. A mini-Neptune is not necessarily Neptune, but adorable. These are size labels, not promises. And when the question is whether humans could ever breathe there, size turns out to matter in surprisingly complicated ways. Let us start with gravity. A larger rocky planet may have stronger surface gravity than Earth. That sounds manageable until you picture daily life under it. Walking becomes harder. Lifting becomes harder. Long-term strain on muscles, joints, circulation and bones could become significant. Human bodies evolved for one Earth gravity, with enough flexibility to tolerate somewhat more or less, but not infinite generosity from physics. A world with 1.3 or 1.5 times Earth gravity might be survivable with adaptation. A world with substantially more could turn stairs into political issues. Children growing up there might adapt differently. Visitors arriving from Earth would notice quickly. Even simple tasks such as standing from a chair could acquire ceremony. On the other hand, a somewhat larger planet might retain atmosphere more effectively. Stronger gravity helps hold gases over geological time. That can be beneficial if the atmosphere is kind. Because gravity does not judge chemistry. A super-Earth could hold a thick, stable, pleasant atmosphere. It could also hold a dense, crushing blanket of carbon dioxide, methane, hydrogen, or compounds best handled by robots. Again, the universe insists on details. Now, consider mini-Neptunes. These planets may possess rocky or icy cores wrapped in substantial atmospheres, many likely formed with thick envelopes of hydrogen and helium that smaller planets either never acquired or later lost. They can be common in observed exoplanet systems, which means many stars may host worlds with plenty of air but none we would enjoy. Hydrogen-rich atmospheres create very different surface conditions depending on pressure, temperature, and depth. Some mini-Neptunes may not have accessible solid surfaces at all in the ordinary sense. Descend through thick atmosphere and pressure rises steadily into states where materials behave strangely, and human settlement plans become theoretical comedy. You cannot build a seaside cottage on a pressure gradient. Still, there are intriguing possibilities. Some scientists have proposed that certain sub-Neptune worlds with moderate temperatures and thick atmospheres might host habitable layers in the atmosphere or deep oceans beneath gas envelopes, depending on composition. Habitable for microbes, perhaps. Habitable for floating civilizations is a sentence best spoken carefully. Let us ground this discussion with real examples. One of the most famous super-Earth candidates is 55 Cancri e. It is larger than Earth and orbits very close to its star, which makes it extremely hot. Far too hot for breathable comfort. Surface or atmospheric conditions are likely severe, with temperatures high enough to melt rock in many models. It demonstrates that Earth-like size ranges do not guarantee Earth-like life. Sometimes bigger simply means hotter and more alarming. Another well-known case is LHS 114OB. This planet has drawn attention because it lies in the habitable zone of a red dwarf star and is dense enough to be plausibly rocky. It is larger and more massive than Earth, making it an interesting candidate for retaining atmosphere over long time scales. Could it have water? Perhaps. Could it have a breathable sky? Unknown. Could gravity feel heavier than Earth? Very likely. Even our most promising candidates remain partly hidden behind distance and limited data. Then there is K2-18b, one of the most discussed mini-Neptune or sub-Neptune worlds in recent years. It lies in a temperate region around its star and has shown atmospheric signals that sparked intense interest, including water vapour detections and later debates about methane, carbon dioxide and possible ocean world scenarios. Some researchers have explored the idea that it could be a Hycean world, meaning a hydrogen-rich atmosphere above a potentially habitable ocean. That is scientifically exciting. It is not the same as saying humans could breathe there. A hydrogen-rich sky with unknown pressure, unknown surface conditions, and possible deep oceans beneath dense atmosphere is many things. Convenient suburban expansion is not among them. Another famous mini-Neptune is GJ1214b. This planet appears larger than Earth but smaller than Neptune, with a low density suggesting significant volatile content or thick atmosphere. It may possess a steam-rich envelope, haze or exotic water-rich interior under high pressures. Again, interesting. Again, not obviously breathable. The discovery of worlds like these changed astronomy because they revealed something our solar system lacks. Intermediate planets are common. Nature does not feel obligated to reproduce our neighbourhood design. This matters for habitability because many stars may host planets in size ranges where atmosphere retention is strong, but surface conditions are ambiguous. A rocky Earth-sized planet with thin atmosphere is one path. A larger planet with thick retained atmosphere is another. Which is better for life? We do not yet know broadly enough. There is a concept worth mentioning here, the radius valley. Observations suggest planets often cluster into smaller rocky worlds and somewhat larger gas-enveloped worlds, with fewer in between. This may reflect atmospheric loss processes. Some planets begin with envelopes and later lose them through stellar radiation, leaving rocky cores. In that sense, a super-Earth might sometimes be a stripped mini-Neptune ancestor. Planets, like people, can have complicated histories. Suppose we found a super-Earth with moderate gravity, oceans, plate tectonics, and an oxygen-nitrogen atmosphere. That would be extraordinary. Stronger gravity might make flight by birds harder, mountains shaped differently, weather circulation altered, and human movement more tiring. But open-air living could still be possible depending on actual values. Trees might grow shorter and sturdier. Athletes would complain with unusual sincerity. Architecture would change. Bones and muscles of settlers born there might differ from ours over generations. Now imagine the opposite. A super-Earth with twice Earth's atmospheric pressure, thick carbon dioxide, dense clouds, and relentless storms. Same size category, completely different lived reality. Categories help organize knowledge, they do not replace measurement. Could mini-Neptunes ever host breathable zones aloft? This is one of those questions that sounds like science fiction until physics reluctantly admits partial interest. If a planet lacks a solid, comfortable surface but has atmospheric layers with suitable temperature and pressure, floating habitats could be imagined in principle. Humans would bring their own oxygen, of course. We would not suddenly become hydrogen-breathing enthusiasts. Still, one could envision engineered aerostats drifting in stable layers of a giant atmosphere, harvesting energy and resources. It would be less planetary colony and more civilized balloon fleet. The emotional challenge should not be underestimated. Many humans like ground. There is also the issue of stellar environment. Many known super-Earths and mini-Neptunes orbit close to their stars because such planets are easier to detect. Close orbits often mean heat, tidal locking, radiation exposure, and atmospheric escape processes. Our catalogue is therefore biased toward dramatic worlds. Calmer, Earth-like distant cases may exist in large numbers and simply be harder to detect. Astronomy is often limited less by reality than by current eyesight. One practical implication for future exploration is that the first truly habitable exoplanet we identify may not fit our intuition perfectly. It might be slightly larger than Earth, under a dimmer orange star with heavier gravity, thicker air, and strange continents. Or it may be a moon around a larger planet, or a water world with scattered archipelagos. Home elsewhere may look unfamiliar. That should be expected. We should also be careful with the phrase better than Earth. Some enthusiasts imagine super-Earths as superior by default. More land, more atmosphere, more gravity, more stability, more everything. But biology often thrives in balanced ranges rather than maximum settings. More gravity strains bodies. More atmosphere may intensify weather or pressure. More mass may sustain volcanism or trap heat differently. More is not a synonym for kinder. Earth's great strength may be proportion. Still, super-Earths remain among the most exciting targets in astronomy, because some could indeed offer long-lived stable environments. Slightly larger mass might preserve internal heat longer, sustaining geology and magnetic fields. Better atmosphere retention might protect oceans. If conditions align, some could remain habitable for immense spans. That is a tempting possibility. Longer windows mean more time for life to emerge and diversify. Mini-Neptunes, meanwhile, challenge us to broaden our thinking about where chemistry and perhaps life can persist. Even if not human homes, they may host exotic environments worth studying deeply. They also remind us that breathable planets might be a minority subset inside a galaxy, rich with other kinds of worlds. Not every destination needs to be ours to matter. From a human settlement perspective, however, the core question remains simple. Can we step outside there? For many super-Earths, maybe someday depending on conditions. For many mini-Neptunes, likely not in the conventional sense. For both groups, we need better data, and that is exactly what modern telescopes are trying to gather. They examine starlight filtered through atmospheres, measure masses and radii, estimate densities, and slowly convert dots into places. Tonight, while many people sleep, telescopes are doing something that would have sounded impossible not very long ago. They're trying to smell the air of other worlds. Not literally, of course. No observatory is leaning dramatically toward the stars and taking a deep breath. Science tends to be less theatrical than that, though not always by much. What astronomers are truly doing is examining faint light from distant stars and asking whether that light carries the fingerprints of gases surrounding planets too far away to visit. This is one of the most astonishing shifts in modern astronomy. We have moved from merely asking whether planets exist around other stars to asking what their skies are made of. And when your topic is whether there are other planets we can breathe on, that question becomes central, because distance prevents easy inspection. We cannot land on these worlds, open a hatch, and file a quick report. Even the nearest exoplanets are vastly farther away than anything humans have ever travelled. So scientists must become detectives of atmosphere using light, motion, timing, and patience. A great deal of patience. Let us begin with the most common technique, transit spectroscopy. When a planet passes in front of its star from our point of view, a tiny fraction of the starlight filters through the planet's atmosphere before reaching our telescopes. Certain gases absorb specific wavelengths of light. By comparing the star's spectrum during transit with the spectrum, when the planet is not in front of it, scientists can infer what gases may be present. In simpler terms, the atmosphere leaves missing lines in the light. Every gas has its own habits. Water vapour absorbs certain wavelengths, methane absorbs others, carbon dioxide, oxygen, sodium, hydrogen, helium, ozone, and many more each interact with light in characteristic ways. The atmosphere becomes readable, not easily readable, mind you. Signals are faint, stars are noisy, instruments have limits, clouds and haze can obscure information, data must be processed carefully. But the principle is extraordinary. A planet dozens or hundreds of light years away can whisper its chemistry through filtered starlight. One of the most famous tools in this effort today is James Webb Space Telescope. Webb is especially powerful for atmospheric studies because many important molecules reveal themselves strongly in infrared wavelengths. Water vapour, methane, carbon dioxide, carbon monoxide, and other compounds often leave clear signatures there. Webb has already studied several exoplanets, including hot giants and smaller worlds, helping refine methods and revealing atmospheric compositions with increasing confidence. This does not mean Webb is finding breathable Earth twins every week. It means we now have instruments capable of serious atmospheric chemistry across interstellar distances. That alone would have stunned earlier generations. What then are scientists searching for? The first category is simple gases that tell us basic planetary nature. Hydrogen and helium often suggest thick primordial atmospheres, more like gas-rich mini-Neptunes than rocky Earth-like surfaces. If a planet is wrapped in deep hydrogen layers, breathable open-air human life becomes unlikely in any familiar sense. Useful discovery, perhaps disappointing picnic news. Next come molecules tied to temperature and climate. Water vapour is one of the most discussed. Detecting water in an atmosphere can indicate humidity, steam, evaporating oceans, or broader chemical cycles. It does not automatically mean surface oceans or beaches with tasteful umbrellas. Water vapour can exist on worlds far too hot, far too cold, or otherwise hostile. Still, water is a promising sign because where water chemistry appears, interesting things often follow. Carbon dioxide matters too. It helps scientists estimate greenhouse potential, atmospheric thickness clues, and planetary evolution. On Earth, carbon dioxide helps keep temperatures suitable. On Venus, enormous carbon dioxide abundance helped create infernal conditions. The molecule itself is not villain or hero, context writes the role. Methane is another major target. Methane can be produced biologically by microbes and larger organisms, but also geologically through non-biological processes. On its own, methane is intriguing but not definitive. In combination with other gases, especially in disequilibrium, it becomes more interesting. This word, disequilibrium, is crucial. An atmosphere left alone tends toward chemical balance. Certain gases react with each other and disappear unless replenished. If scientists detect combinations that should not coexist for long without continuous replacement, they ask what process is maintaining them. Life is one possibility. Geology is another. Unknown chemistry is a third. Caution remains mandatory. Oxygen receives enormous public attention because humans are sentimental about breathing. If astronomers detect substantial oxygen in a rocky planet atmosphere, headlines understandably become excited. Yet oxygen is not automatic proof of life. On Earth, oxygen abundance is strongly linked to biology, especially photosynthesis. But oxygen can also accumulate through abiotic pathways. For example, intense stellar radiation may split water molecules. Hydrogen escapes to space more easily, leaving oxygen behind. That can produce oxygen-rich atmospheres on dry or damaged worlds. A planet can have oxygen and still be miserable. Again, astronomy teaches humility. Ozone, a molecule made of 3 oxygen atoms, is also important. Ozone can indicate oxygen chemistry and provides ultraviolet shielding on Earth. Detecting ozone may sometimes be easier than detecting oxygen directly depending on wavelengths and instrument capabilities. Scientists often think in packages rather than single clues. Oxygen plus methane together can be particularly compelling because they tend to react away over time. If both are abundant simultaneously, some active replenishment is implied, not proof. But interest rises sharply. Then there are aerosols, clouds, and hazes. These may sound secondary, but they can dominate what telescopes see. Thick haze layers can flatten spectral signals and hide deeper atmospheric composition. Titan demonstrates how haze can transform appearance and chemistry. Some exoplanets likely wear global haze coats that frustrate observers magnificently. Clouds can also reveal climate patterns and energy balance. Water clouds, sulfur compounds, mineral clouds, even metal vapor condensation on ultra-hot worlds may occur depending on temperature. Yes, some planets likely have weather reports best read from a safe distance. Another major target is temperature itself. By observing infrared emission when a planet passes behind its star or through orbital phases, scientists estimate dayside and nightside temperatures. This helps reveal heat transport, atmospheric circulation, and whether a planet may be tidally locked with one permanent hot face. A planet with strong atmosphere may move heat efficiently. A stripped rocky world may show extreme contrasts. Temperature maps from light curves would have sounded like wizardry a century ago. Now they are research papers. Let us ground this with real examples. HD 209-458b became historically important because sodium was detected in its atmosphere, one of the first atmospheric detections for an exoplanet. HD 189733b has been studied extensively for water vapor, weather patterns, and haze. K2-18b has drawn enormous attention because data suggests molecules such as methane and carbon dioxide, with debates over ocean-world interpretations. WASP-39b became a notable early James Webb target showing clear carbon dioxide signatures and detailed atmospheric characterization. These are not breathable Earths, they are stepping stones. Scientists practice first on larger, easier targets because giant atmospheres produce stronger signals. Studying hot Jupiters and warm sub-Neptunes teaches methods later needed for small rocky worlds. It is like learning to hear whispers by first studying drums. What makes Earth-like atmospheres hard to detect? Several reasons. First, Earth-sized planets are small relative to their stars, so they block less light during transit. Second, thin atmospheres produce subtle signals. Third, many target stars are far away or noisy. Fourth, clouds can hide signatures. Fifth, repeated observations are often needed, consuming precious telescope time. This is why planets around small stars receive special attention. A rocky planet crossing a small red dwarf blocks a larger fraction of the star's light, making detection easier. Systems like TRAPPIST-1 are therefore prized laboratories. Of course, red dwarfs bring their own flare-related complications. The universe dislikes free lunches. Scientists also search for atmospheric escape. Ultraviolet observations can reveal hydrogen streaming from planets losing upper atmospheres. This tells us how stars erode worlds over time. Some planets may be transformed dramatically by long-term atmospheric loss. Others may be left bare. There is another subtle thing astronomers seek: pressure clues. Pressure is difficult to measure directly at distance, but certain spectral broadening effects, scattering behaviours, and climate models can constrain possibilities. Pressure matters enormously for your topic, because breathable chemistry without adequate pressure still fails human lungs. A planet with oxygen traces in near vacuum is not our destination. One with suitable pressure and chemistry would be far more exciting. Future missions may push further. Concepts for direct imaging telescopes aim to block starlight and photograph planets directly, separating faint planetary light from overwhelming stellar glare. With such tools, scientists could study reflected light from Earth-like planets and search for oceans, continents, seasonal changes, clouds, and biosignature gases. Imagine seeing pale blue dots around other suns and analysing their skies. That future is being built piece by piece. Still, caution must remain our companion. Public enthusiasm often leaps from one tentative molecule to alien life discovered. Real science moves slower. Signals can be ambiguous. Instrument systematics exist. Models differ. Independent confirmation matters. Patience is not a flaw here. It is professionalism. What scientists search for tonight, then, is not merely oxygen or water. They search for stories. Did this planet keep its atmosphere? Did its star strip it bare? Is there greenhouse warming, cloud decks, chemical imbalance, possible oceans, volcanic replenishment, biological hints, or only sterile gas under unfamiliar light? Every spectrum is a biography in fragments. And somewhere among thousands of worlds, there may be one whose data begin to resemble home. Moderate temperature, stable pressure clues, water signatures, oxygen, methane tension, cloud cycles, perhaps seasons. Not certainty, but invitation. Until then, the atmosphere around you remains the only one known to support unprotected human breathing. It is easy to forget how scientifically impressive that is. If Earth were observed from far away, astronomers would find it astonishing. Oxygen, water vapour, methane traces, clouds, oceans, disequilibrium chemistry, changing seasons, reflective continents, living pigments. We are the exotic targets someone else might hope to find. If humanity has a list of distant addresses it keeps glancing at, hopefully this would be it. For centuries, planets around other stars were imagined, debated, guessed at, and occasionally argued over with impressive confidence and very little data. Then, in the last few decades, everything changed. We began detecting them in large numbers. Not one or two curiosities, but thousands. Hot giants, scorched rocks, compact systems, strange mini-Neptunes, worlds on eccentric orbits, worlds circling twin stars, worlds unlike anything in our own solar system. Somewhere within that growing catalogue, a natural question emerged. Which ones look most promising? Not confirmed second Earths. We do not have one of those yet. No telescope has shown us alien forests, breathable valleys, or a neighbour hanging laundry beneath another sun. But several exoplanets stand out as especially interesting because of size, orbit, star type, likely composition, or relative closeness. These are not guarantees, they are the short list of possibility, and possibility when measured across light years is already extraordinary. Before we begin, it helps to remember what promising means here. Usually it refers to worlds that may be rocky, may receive suitable stellar energy for liquid water, may retain atmospheres, and orbit stars close enough or quiet enough for future study. It does not mean pack your bags. Interstellar luggage remains premature. Let us begin with perhaps the most famous nearby candidate, Proxima Centauri b. This planet orbits Proxima Centauri, the closest star to our solar system, at just over 4 light-years away. In cosmic terms, that is next door. If stars were houses on a street, Proxima would be the neighbour whose lights you notice through the curtains. Proxima Centauri b is roughly Earth mass scale, and lies in a region where temperatures could allow liquid water under the right atmospheric conditions. That combination alone made headlines worldwide. But then reality arrived carrying caveats. Proxima Centauri is a red dwarf star, and like many red dwarfs it can be active, producing flares and energetic radiation. A close-orbiting planet may face atmospheric erosion or difficult surface conditions. The planet may be tidally locked, meaning one side always faces the star. Could it still host atmosphere and habitable regions? Yes, possibly. Could it be barren and stripped? Also possible. Proxima Centauri b is promising because it is near, Earth-sized in broad terms, and worthy of intense future study. It is not promising because it is easy. Next, we should visit one of the most beloved systems in modern astronomy, TRAPPIST-1. TRAPPIST-1 hosts 7 known roughly Earth-sized planets in a compact system. Several of them orbit within or near the star's habitable zone, especially TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g. This system feels almost designed to attract scientific affection. Multiple rocky worlds, transit geometry ideal for atmospheric study, nearby enough to observe comparatively well, a chance to compare several planets formed around the same star under different energy inputs. TRAPPIST-1e is often highlighted as one of the strongest candidates for a potentially temperate rocky world. Density estimates suggest a rocky composition, and its orbit places it in a favourable region for possible liquid water depending on atmosphere. Yet again, the host star complicates matters. Red dwarf activity, tidal locking, atmospheric retention, and water history remain open questions. Still, if you asked many astronomers for a top-tier target list, TRAPPIST-1e would likely appear quickly. Then there is LHS-114OB. This planet orbits a relatively nearby red dwarf and has attracted strong interest because it appears dense enough to be rocky and lies in the star's habitable zone. It is larger and more massive than Earth, making it a super-Earth candidate. Why is that exciting? Its higher mass may help it retain atmosphere over long timescales. If the host star is calm enough and conditions favourable enough, it could represent a durable habitable environment. Some studies have even suggested possible ocean world scenarios or thick atmospheres worth future examination. Would gravity feel heavier there? Very likely. Would humans breathe there comfortably? Unknown. Would scientists love better data? Immediately. Now let us consider Kepler 186f. This was historically important as one of the first Earth-sized planets found in the habitable zone of another star. It orbits a red dwarf farther away than our nearest candidates, so detailed follow-up is harder, but its discovery was a milestone. It proved that small, potentially temperate planets exist. Sometimes significance lies not only in present usefulness, but in opening doors. Kepler 186f helped move the conversation from "do such worlds exist?" to "how many might there be?" Another frequently mentioned candidate is Kepler 452b. This world orbits a Sun-like star and gained attention as a possible older, larger cousin to Earth. It receives somewhat similar stellar energy to Earth, though it is likely larger than our planet. Whether it's truly rocky, partly gaseous, or otherwise unlike Earth remains uncertain. Still, planets around Sun-like stars are especially compelling because our own experience tells us such stars can host long-lived habitable worlds. Distance, however, makes close characterization difficult. A more recent and exciting nearby system includes TOI 700d and TOI 700e. These planets orbit a relatively nearby small star, and some lie within conservative or optimistic habitable zones depending the model used. TOI 700d in particular received attention as an Earth-sized candidate in a temperate orbit. Later discoveries in the same system increased interest because multiple, potentially interesting worlds around one nearby star create valuable opportunities for comparison. Again, nearby matters. The closer the system, the better our chances of future atmospheric study. What makes these planets most promising compared with thousands of others? Usually some combination of 5 things. First, size. Rocky worlds roughly Earth-sized or somewhat larger are more appealing than gas giants if the goal is surface habitability. Second, orbit. Receiving the right amount of stellar energy matters for potential liquid water. Third, star type. A stable star improves long-term prospects. Fourth, distance from us. Closer systems are easier to study. Fifth, observational geometry. Planets that transit their stars are especially valuable because atmospheres may be analysed through spectroscopy. Even with these advantages, uncertainty remains enormous. We often know a planet's radius, mass estimate, orbital period, and some stellar properties. We may infer density, we may model climate scenarios, but we usually do not know the exact atmosphere, cloud cover, surface geography, ocean presence, plate tectonics, biosphere status, or whether alien equivalents of mosquitoes exist. The last point alone justifies caution. There is another subtle issue. Promising can change with better data. A planet once celebrated as potentially habitable may later appear too gaseous, too hot, too irradiated, or lacking atmosphere. Another overlooked world may rise in status after improved measurements. Science is not a parade of final answers. It is a ranking system under constant revision. That is healthy. It means evidence still matters. Why have we not yet found an unquestionable Earth twin? Partly because Earth twins are hard to detect. Small rocky planets around sun-like stars produce tiny signals. Long orbital periods require patience. Thin atmospheres are difficult to characterize. Our tools are improving rapidly, but this remains technically demanding work. We found the loud easy cases first. Hot giants close to stars, inflated planets, dramatic transits. Now we are learning to hear whispers. That is why missions like James Webb Space Telescope matter so much. Webb and future observatories can study atmospheres of some promising candidates, searching for gases, clouds, and clues to habitability. The next generation of giant ground telescopes and proposed direct imaging space missions may push further still. One day, we may move from promising to persuasive. Until then, these worlds occupy a special place in culture. They are scientific objects, yes, but also mirrors for human hope. We project onto them questions about loneliness, destiny, migration, survival, and belonging. Could somewhere else sustain us? Could life be common? Could Earth be typical? Could home happen twice? No exoplanet has answered those questions fully yet, but every promising candidate narrows the mystery. There is also something humbling about the list. Even our best options are difficult. Proxima Centauri b may be storm-battered. TRAPPIST-1 worlds may struggle with stellar activity. Super-Earths may have heavy gravity or thick air. Some candidates are dozens or hundreds of light years away. The galaxy does not seem eager to hand us a simple duplicate. That may be for the best. Easy answers can make species careless. Instead, we are being asked to learn more deeply about atmospheres, stars, geology, biology, and the extraordinary set of conditions Earth already provides. Because every time we rank promising distant planets, we quietly compare them to something very specific. Blue oceans, moderate sky, liquid rain, usable pressure, oxygen-rich air, long stability, life in abundance. We compare them to home. If no nearby world offers breathable air for free, the next human instinct is predictable. We ask whether we can make some. This is a very human response to difficulty. When nature does not provide a path, we build one. We tunnel through mountains, drain wetlands, irrigate deserts, heat homes in winter, cool them in summer, grow food in glass houses, cross oceans in metal, and place machines in orbit because gravity seemed overly confident. So when we look at Mars, the Moon, icy moons, or distant planets with hostile skies, it is almost inevitable that someone asks, could we change the atmosphere? Could plants, microbes, or machines make alien air for us? This broad idea is often called terraforming when applied at planetary scale. The word is famous, dramatic, and wonderfully efficient at hiding complexity. It sounds as though one might arrive with tools, unfold a brochure, and begin converting a planet by Tuesday. Reality prefers longer timelines. Still, the concept deserves serious thought because it sits at the intersection of planetary science, biology, engineering, ethics, and patience. Great patience. Let us begin with the simplest distinction. There are two very different goals often blended together. First, creating breathable environments locally. Second, changing an entire planet globally. The first is difficult but plausible. The second may be one of the largest engineering challenges imaginable. Suppose humans settle Mars. We do not need to terraform all of Mars before anyone lives there. We could build habitats, domes, underground bases, tunnels, or pressurized valleys covered by membranes. Inside these spaces, air could be manufactured and recycled. Crops could grow, water could circulate, microbes could help process waste and nutrients. This is artificial atmosphere on a local scale, much more realistic. We already practice versions of it in spacecraft and stations. NASA, ESA, and other agencies have decades of experience maintaining closed life support systems where breathable air is not naturally available. Every crewed spacecraft is a tiny world with managed weather. The challenge is scaling. A 6-person station is one thing, a city of 100,000 is another. Now let us consider biology. Plants are often the first suggestion because they are visually reassuring. Put trees on Mars, people say. Add forests. Let leaves do the work. This is charmingly optimistic. Plants use photosynthesis to convert carbon dioxide and water into sugars, releasing oxygen. On Earth, photosynthetic life has profoundly shaped our atmosphere over geological time. So why not repeat the trick elsewhere? Because plants are demanding collaborators. They need liquid water, nutrients, suitable temperatures, light, pressure ranges, and protection from radiation or extreme chemistry. A tree does not simply stride onto Mars, salute the horizon, and begin terraforming. Mars today is cold, dry, irradiated, low pressure, and nutrient challenging. Unprotected terrestrial plants would fail quickly. Before plants can help, we must already solve many environmental problems. That means habitats first, biology second. Still, controlled greenhouses on Mars are plausible and likely essential. Plants could provide food, oxygen contribution, humidity management, psychological comfort, and carbon dioxide removal within settlements. The first Martian forest, if it happens, may begin as a very expensive greenhouse. Microbes may be more realistic pioneers than plants. Microorganisms tolerate extremes better than trees generally do, and they are astonishingly versatile. Some survive intense cold, radiation, acidity, dryness, salt, and nutrient scarcity. Extremophils on Earth inhabit hot springs, Antarctic ice, desert rock, deep crust, and toxic ponds whose tourism appeal is limited. Could engineered microbes be used on alien worlds? Possibly. Microbes might help release nutrients from regolith, produce useful gases, stabilize soils, generate biofuels, recycle waste, or slowly alter enclosed environments. Cyanobacteria, which helped oxygenate early Earth, often appear in terraforming discussions because they use sunlight and carbon dioxide. But again, context matters. Even microbes need water and survivable conditions. On Mars, outdoor deployment faces cold, UV radiation, and low pressure. Protected bioreactors may be more practical than simply sprinkling microbes heroically across the landscape. Machines, meanwhile, may be the real first movers. Machines do not require oxygen. They can operate in vacuum, cold, toxicity, and monotony. They can mine ice, process regolith, extract oxygen, build structures, bury habitats for radiation shielding, assemble solar arrays, and maintain systems long before large populations arrive. Robots are excellent early colonists because they rarely ask how long until lunch. On Mars, one promising route is extracting oxygen directly from atmospheric carbon dioxide. This has already been demonstrated experimentally by Perseverance through the MOXIE device, which converted Martian CO2 into oxygen. Small scale, yes, symbolically enormous. It showed that local resources can become life support. Water electrolysis is another path. If ice is available, splitting water into hydrogen and oxygen provides breathable oxygen and fuel components. Many future settlement plans rely heavily on this principle. Bring power, find water, make air. Simple sentence, very large project. Now let us discuss full planetary terraforming, because the word tends to wander into every conversation. Mars is the most common candidate. It has a day length similar to Earth's, accessible water ice, tolerable gravity compared with the Moon, and a surface humans can use. The dream usually proceeds as follows: warm Mars, thicken the atmosphere, melt ice, release trapped gases, introduce biology, wait. Then eventually walk outside. Unfortunately, each step contains many hidden steps. Current research suggests Mars may not possess enough easily accessible carbon dioxide in ice caps and soil to create Earth-like atmospheric pressure simply by releasing what is already there. Even if all known reservoirs were mobilized, results may still fall far short of breathable pressure. You cannot terraform with gases you do not have. Could additional volatiles be imported? In principle, perhaps. Redirect comets, process asteroids, deliver manufactured gases, but the scale would be staggering. Civilization-level industry over centuries or millennia. Terraforming Mars is less a project than an era. What about Venus? Venus has the opposite problem. Too much atmosphere, too much heat, mostly carbon dioxide, crushing pressure. Terraforming Venus would require cooling the planet massively, removing or chemically locking away enormous atmospheric carbon dioxide inventories, perhaps adding water, and managing a rotation pattern that is leisurely in the extreme. Mars asks for more air. Venus asks for less everything. Neither is impossible in pure imagination. Both are formidable in physics. Then there are moons such as Titan. Titan already has thick atmosphere but no oxygen and brutal cold. You might prefer habitat engineering there rather than global conversion. Similarly, moon colonies would likely rely on sealed environments rather than trying to create and retain a global atmosphere the moon's gravity would struggle to keep. This suggests a broader truth. Artificial local worlds may beat planetary transformation for a very long time. Instead of changing Mars entirely, build cities under domes. Instead of warming Europa, carve shielded habitats in ice. Instead of remaking Titan, create enclosed warm districts. Instead of altering the sky, build under it. This is more modular, more controllable, and much faster. There is also the issue of time. Earth's oxygen-rich atmosphere was shaped over billions of years by microbial life, oceans, rocks, burial of carbon, and feedback cycles. Humans may accelerate processes dramatically with technology, but even then, planet-scale atmospheric change may take centuries or longer. Civilizations struggle to plan next quarter. Terraforming asks for 10,000 quarters. That does not make it foolish. It makes it civilizational rather than entrepreneurial. There are ethical questions too. If Mars hosts dormant microbial life or hidden ecosystems, should we overwrite them? If Europa's ocean contains native biology, do we have the right to contaminate it? Even sterile worlds may possess scientific value in their untouched states. A planet is not merely empty land because no one is there to file paperwork. Future generations may debate preservation versus transformation intensely. There is another practical challenge often ignored: maintenance. Suppose you successfully create breathable pockets on Mars. Great success. Then dust storms damage power systems, seals age, microbial contamination spreads, crop disease hits, supply chains fail, politics intervene, or simple neglect appears. Nature maintains Earth's atmosphere through planetary systems. Artificial atmospheres need operators forever, or at least for as long as residents enjoy breathing. Still, the idea remains compelling because pieces of it are already real. Closed-loop air recycling, hydroponic agriculture, bioregenerative life support, CO2 scrubbing, water recovery, oxygen generation, habitat pressure systems, robotic construction. These are not fantasies, they're engineering domains advancing now. The first terraforming humans experience elsewhere may be a hallway lined with lettuce under LED lights, and that would count. Psychologically, plants may matter beyond chemistry. Green life calms people. Studies on Earth show benefits from greenery, gardens, and natural forms. In sealed habitats, a patch of moss or a tomato vine may do emotional work no machine can replicate. Sometimes oxygen is not the only thing leaves provide. Could machines one day build giant atmospheric processors on Mars, releasing greenhouse gases to warm it gradually? Perhaps. Could orbital mirrors redirect sunlight? Possibly in principle. Could genetically engineered microbes assist in prepared environments? Conceivably. Will any of this happen soon? Unlikely at full planetary scale. Will local artificial atmospheres happen if humans settle beyond Earth? Almost certainly. And perhaps that is enough for now. We often dream in planet-sized terms because it feels grand. But civilization usually advances through rooms, farms, factories, tunnels, stations and neighbourhoods before continents. A breathable city on Mars would be more historic than a theoretical future breathable planet. One real dome beats 1,000 speeches. There is a final emotional layer here. Terraforming is often presented as making another world more like Earth. Yet perhaps the deeper task is carrying Earth-like systems with wisdom. Clean air, cycling water, living soil, resilient ecosystems, balanced chemistry, stewardship. Those are difficult enough here already. If we cannot manage atmosphere responsibly on our home planet, exporting confidence may be premature. Still, hope has its place. Somewhere ahead, children may grow up inside settlements where the air was manufactured by machines, refreshed by algae, sweetened by gardens, and guarded by engineers no one thanks enough. They may look through windows at hostile landscapes and think of breathable rooms as ordinary, just as we think of Earth's sky now. Suppose tomorrow astronomers announce something extraordinary. A nearby rocky planet, perhaps orbiting a calm orange star, has an atmosphere with usable oxygen, tolerable pressure, moderate temperatures, liquid water, and no immediately obvious chemical hostility. After years of cautious study, the evidence becomes stronger. This world appears, by every remote test available, breathable. For a few glorious hours, humanity would lose all ability to behave normally. Headlines would sprint, governments would schedule speeches, investors would become emotional, artists would begin sketching alien coastlines. Someone would try to sell commemorative mugs before lunch. Scientists, meanwhile, would continue speaking carefully, while everyone else replaced nuance with fireworks, and beneath all the excitement would sit a deeper question. If we found a breathable planet, could we truly live there? Notice the shift. Not survive there, not land there, not build a base there, live there. That is a much harder question. Because breathable air, while essential, is only one layer of home. It may be the first requirement, but it is nowhere near the last. A planet can let your lungs function and still challenge everything else about being human. We sometimes imagine colonization as a chemistry problem. Get oxygen right, pressure right, temperature right, water available, and the rest will sort itself out. History suggests otherwise. Humans do not merely inhabit environments, we inhabit systems. Ecological, social, emotional, cultural, agricultural, medical, architectural, psychological, and symbolic. We need more than air. We need continuity, meaning, trust, food webs, institutions, stories, routines, and places where children can grow without every generation reinventing plumbing. Let us begin with biology. Even on a breathable world, gravity matters. If surface gravity were significantly higher than Earth's, bodies might struggle. Movement becomes more tiring, cardiovascular strain rises. Long-term stress on joints, bones, and circulation could change health outcomes. Pregnancy and development might be affected in ways we do not yet understand. Athletic records would become aggressively local. If gravity were much lower, another set of problems appears: muscle loss, bone loss, altered fluid distribution, balance changes, and developmental concerns emerge. We know from spaceflight that human bodies respond strongly to changed gravity. So yes, you might breathe comfortably. You may also hate stairs for entirely new reasons. Day length matters too. A planet rotating every 10 hours or every 70 hours would reshape sleep, agriculture, work rhythms, weather patterns, and circadian biology. Humans can adapt to shift work poorly enough on Earth. Imagine explaining a 40-hour daylight period to your nervous system. Seasonality matters, axial tilt matters, light spectrum matters. A planet orbiting a redder star may bathe landscapes in different colours and rhythms. Plants adapted there, if any exist, might use different pigments. Human psychology responds to light in subtle ways. Mood, hormones, sleep cycles, perception, and architecture would all be affected. Then there is food. A breathable atmosphere does not guarantee edible ecosystems. Native life, if present, may be biochemically incompatible, indigestible, allergenic, toxic, or nutritionally useless to us. Even if harmless, local plants may not provide needed amino acids, fats, vitamins, or minerals in accessible forms. The first settlers would likely rely heavily on imported crops, controlled agriculture, hydroponics, and familiar microbial systems, which means breathable planet still may begin as greenhouse civilization. Could Earth crops grow there? Perhaps, but soil chemistry, microbes, seasons, pests, trace metals, and local weather would matter enormously. Earth agriculture is not a seed packet plus optimism. It is a long coevolution between plants, climates, soils, fungi, insects, and human management. A new planet would demand learning everything again. Water quality also matters. Liquid water may exist, but with what salts, microbes, dissolved compounds, pH, and seasonal behaviour? A beautiful lake may require treatment before drinking. Rivers may flood strangely under unfamiliar gravity and terrain. Ice cycles may differ. Rain patterns may be erratic. Then comes disease. If alien life exists, it may not infect humans at all because biochemistry could be too different. That is often noted and perhaps reassuring. But it could still trigger immune reactions, toxins, environmental inflammation, or ecological disruption. Meanwhile, Earth microbes carried by settlers may become their own problem in closed communities or fragile new ecosystems. Even without aliens, medicine on another world is hard. Supply chains are long, specialists are few, emergencies become serious quickly. Surgery during communication delay and limited resources acquires drama no one requested. Psychology may be even more underestimated. Humans evolved under open skies, familiar landscapes, ancestral cues, changing weather, birdsong, oceans, insects, wind through leaves, and social worlds rich with history. A new planet may offer beauty, but also profound estrangement. Different constellations, different sunsets, different smells, or none. Different horizons, no inherited memory attached to rivers or mountains. That sounds romantic for a week and disorienting over decades. Home is partly atmosphere. It is also recognition. Would children born there feel differently? Almost certainly. They would grow up with that sky as normal. They would know its seasons, slang, dangers, jokes, architecture, and school calendars. They might consider Earth picturesque but oddly heavy, crowded, and sentimental. The first generation settles a frontier. The second generation calls it ordinary. This has happened repeatedly in human history on smaller scales. Culture would diverge quickly. Language shifts. Food traditions adapt. New holidays appear based on orbital cycles. Art reflects local moons and weather. Politics reorganizes around distance and self-reliance. A colony becomes a society, then a civilization. Air was only the opening chapter. There is also the issue of law and conflict. Who owns land on a new world? How are resources shared? What rights do settlers have relative to sponsoring nations or corporations? How are disputes resolved when help is years away? How much autonomy does distance create? Human beings can turn excellent environments into difficult places through governance alone. A breathable planet does not automatically solve that. Now let us consider distance, because this may be the sternest reality of all. Most promising exoplanets are many light years away. With current technology, travel would take immense timescales. Even optimistic future propulsion concepts imply generations, suspended systems, or technologies not yet demonstrated. So if we found a breathable exoplanet, we might know it exists long before we could reach it. It could become less a destination than a mirror for hope. Mars, by contrast, is reachable in months, yet not breathable. A nearby harsh world may be more practical than a distant paradise. This creates a poignant tension. The best home may be too far. The closest homes may not be homes yet. Could we truly live on a breathable planet if it were reachable? Possibly, but only by building more than shelters. We would need schools, hospitals, agriculture, energy systems, governance, art, recreation, grief rituals, maintenance cultures, archives, childcare, repair skills, waste cycles, and social trust. Civilization is infrastructure plus meaning. Many colonization fantasies imagine rugged pioneers with tools and determination. Real societies are built by plumbers, teachers, nurses, electricians, administrators, farmers, mechanics, coders, parents, and people who remember where the spare parts are stored. The heroic age lasts briefly. Then someone must organize garbage collection. There is also identity. Would settlers still think of themselves as Earth citizens, as planetary nationals, as something new entirely? History suggests new places generate new loyalties. Distance hardens this. Shared hardship accelerates it. A breathable planet may become truly livable only when it stops being the colony and becomes home. That transition is emotional, not chemical. Suppose no native life exists, then ethical concerns center on stewardship and self-governance. Suppose native life does exist, even microbial. Everything changes. We would face obligations not to erase a second genesis casually. Human settlement might need strict protected zones, biological containment, or decisions to remain offshore, so to speak, in orbital habitats rather than surface sprawl. The presence of life turns colonization into coexistence. Would many people actually want to move? Some certainly would. Humans contain explorers, builders, idealists, escape artists, romantics, scientists, and those who simply enjoy a difficult project. But many would not. Earth offers oceans, culture, families, history, biodiversity, breathable forests, and pizza delivery in some regions. Leaving that behind permanently is not a trivial lifestyle choice. Another subtle issue is nostalgia. The first settlers may spend years missing rain that smells like Earth rain, gravity that feels like Earth gravity, birds that sound like Earth birds, trees that evolved in Earth wind. Even success may carry homesickness. Civilization elsewhere may need rituals of remembrance. Yet over time, something beautiful could happen. People would plant parks adapted to local conditions. Streets would gain names with stories behind them. Children would race under that alien sky and complain about homework. Local music would emerge. New myths would form around first landings, first harvests, first storms survived. Human meaning would root itself again. We are good at that. So could we truly live there? Yes, perhaps. But not because the air is breathable. Because humans can turn survivable places into meaningful ones when given time, cooperation, and enough functioning maintenance systems. The atmosphere gets you out the door, community keeps you there. This realization circles us back toward Earth in a surprising way. Our own planet is not merely breathable, it is already layered with memory, ecosystems, language, history, roads, gardens, grief, beauty, mistakes, music, and generations of accumulated belonging. Another world might one day become home. This one already is. After spending so much time looking outward, comparing planets, stars, atmospheres, oceans, and possibilities, something unexpected often happens. Earth begins to look stranger. At first, astronomy can make our planet feel ordinary. We orbit one star among hundreds of billions in a galaxy among perhaps trillions of galaxies. We are not at the geometric centre of anything obvious. We are not the largest world, the hottest, the oldest, the brightest, or the most dramatic. Cosmic perspective can shrink human vanity very efficiently. Then the details arrive, and the details suggest a different kind of importance, not centrality, rarity. This does not mean Earth is certainly unique. Science does not know that. It would be an overstatement to claim we are alone or singular based on current evidence. The universe is far too large for casual absolutes, but it may be increasingly reasonable to suspect that the full package Earth represents is less common than many early optimists assumed. Not a rocky planet, not merely a planet in a habitable zone, not just liquid water somewhere, the full package. A world with long-term surface oceans, stable climate ranges, active geology, retained atmosphere, protective shielding, rich chemistry, abundant biodiversity, complex multicellular life, oxygen-rich air, and billions of years of continuity sufficient for intelligence and civilization to emerge. That combination may be hard to assemble. Let us begin with something simple. Planets are common, but useful planets are a narrower category. We now know the galaxy is crowded with worlds. Thousands of exoplanets have been confirmed, and many more almost certainly exist. Some stars host tightly packed systems, some have giants, some have rocky worlds. Planet formation appears normal rather than exceptional. This is exciting. But common ingredients do not guarantee common outcomes. Sand is common, castles are not. Many discovered planets are hostile by human standards. Hot Jupiters skimming their stars, scorched rocks, frozen bodies, gas worlds with no surface, mini Neptunes with thick hydrogen envelopes, planets on eccentric orbits with severe climate swings, worlds likely stripped of atmosphere, or planets orbiting flare-active stars. Interesting is common. Comfort is not. Consider star type. Small red dwarfs are the most common stars in the galaxy. That sounds hopeful until we remember many are active, especially in youth, producing flares and radiation that may challenge atmospheric retention on close-in planets. Their habitable zones lie near the star, increasing tidal locking and exposure concerns. Larger, hotter stars may be calmer in some ways, but often live shorter, stable lives, perhaps limiting time for complex evolution. Sun-like stars and certain K-dwarfs may offer especially favourable balances, but they are not the majority. Already the field narrows. Then there is planetary placement. A world too close to its star may lose water or suffer runaway greenhouse heating. Too far and oceans freeze unless greenhouse warming compensates. Orbit shape matters too. Strong eccentricity can create severe cycles. Giant neighbouring planets may destabilise orbits, or occasionally help shield inner worlds, depending on system architecture. A stable temperate orbit across billions of years may be valuable. Earth has had one. Atmosphere retention is another filter. Small planets can lose atmospheres over time. Worlds without magnetic protection may suffer enhanced stripping. Internal geology matters because volcanism and tectonics can replenish gases and regulate climate. Without active recycling, a planet may become geologically quiet and climatically brittle. Earth is not merely sitting in good sunlight, it is running planetary maintenance. Water deserves its own category. Surface liquid water appears foundational for all known life. Yet maintaining oceans over immense timescales requires the right temperatures, enough initial water inventory, atmospheric pressure, and resistance to catastrophic loss. Some worlds may begin wet and dry out, others may freeze deeply, others may bury water under ice shells. Earth keeps water openly accessible on the surface. That may matter more than we casually admit. Then comes life itself. Microbial life, if common, may arise in many niches, but the path from microbes to forests, fish, insects, mammals, and technologically curious apes is another matter entirely. On Earth, simple life emerged early. Complex multicellular life took much longer. Intelligence capable of engineering took longer still. This suggests that even if life begins often, advanced ecosystems and civilizations may require rare persistence. Time without total reset. Enough stability to experiment biologically for eons. Enough challenge to drive adaptation. Enough luck to survive extinctions. Earth has endured asteroid impacts, ice ages, supervolcanoes, oxygen shifts, continental rearrangements, and mass extinctions, yet life repeatedly recovered and diversified. That resilience may be exceptional. Let us discuss oxygen, because for your topic it matters deeply. Earth's breathable atmosphere is not primordial. It was transformed by life, especially photosynthetic microbes and later plants. Free oxygen is reactive and tends not to accumulate in large amounts without sustained replenishment. Many planets may host life and still lack oxygen, rich skies for long periods. A living world need not be a breathable world. That distinction may remove many candidates from the human home list immediately. Even Earth nearly did not provide this luxury for most of its history. If humans had appeared billions of years earlier, we would have been disappointed. There is also the Moon. Our large moon likely helps stabilize Earth's axial tilt over long timescales. More stable tilt may moderate extreme climate chaos and preserve regular seasonal patterns. The Moon also shaped tides, coastal environments, and perhaps ecological opportunities in deep history. Is a large moon required for complex life? Unknown, but Earth has one. Another item on the suspiciously helpful list. Plate tectonics may be rare or intermittent elsewhere. We do not yet know. On Earth, moving plates recycle carbon, build continents, create varied habitats, and maintain long-term climate feedbacks. Continents themselves may matter by creating shallow seas, coastlines, nutrient cycles, and environmental diversity. Our world is not one giant ocean, not one giant desert, not one static crust. It is varied and restless. Variation can be biologically productive. Then there is the timeline of the host star. Sun has been stable enough for billions of years. Not perfectly constant, but stable enough. A star that changes too fast, flares too violently, or dies too soon may interrupt complexity before it matures. Life may need not only a stage, but a patient spotlight. Now consider observational bias. We often hear about exciting exoplanets, but many easiest to detect worlds are the dramatic ones. Large planets close to stars, frequent transits, strong signals. Quiet Earth analogues are harder to find. This means our current catalogue underrepresents some gentle worlds. That is hopeful. But even accounting for bias, the sheer diversity of hostile worlds reminds us that being a planet is easy compared with being Earth-like. There is also a philosophical trap worth avoiding. When we say Earth seems rare, we must remember observer bias. Of course, we find ourselves on a world capable of producing observers. We could not wake up on a sterile lava ball and complain about it. Any beings asking this question will likely inhabit one of the rare successful cases. This is known broadly through anthropic reasoning. It is sensible, but incomplete comfort. Even if observers necessarily arise on habitable worlds, those worlds may still be genuinely uncommon. Imagine lotteries. Every winner necessarily holds a winning ticket, but winning tickets can still be rare. Another striking point is cultural. We often speak as though humanity has outgrown dependence on nature. Yet every supply chain, city, hospital, data center, and aircraft ultimately rests on a biosphere and atmosphere functioning reliably. Soil fertility, Pollinators, climate patterns, freshwater cycles, breathable air, ocean chemistry and biodiversity remain foundational. Technological civilization is not separate from Earth systems, it is built on top of them. This matters because looking for another breathable world can accidentally make home seem replaceable. In reality, even if 10 suitable exoplanets exist, they are light years away. Earth is available now, already functioning, already inhabited by everything we know. Rarity plus immediacy is a powerful combination. Could there be countless Earths hidden among the stars? Possibly. Could microbial worlds be abundant while breathable civilization worlds remain scarce? Also plausible. Could Earth be one of many but still rare enough that each example is precious? Very plausible indeed. Perhaps rarity should not be framed only statistically. Even if Earth-like planets are numerically common in a galaxy of hundreds of billions of stars, each one may still be separated by immense distances and independent histories. Common in percentage terms and precious in practical terms can both be true. A million gems scattered across an ocean remain hard to reach. There is also the emotional effect of studying other worlds. Every time astronomers announce a promising candidate, we learn new caveats. Too hot, too cold, too thick an atmosphere, too thin an atmosphere. Too active a star, too much radiation. Likely ocean but buried under ice. Probably gaseous. Unknown composition, tidal locking concerns, distance frustratingly large. Meanwhile, Earth quietly continues offering oceans, forests, nitrogen-rich pressure, oxygen abundance, moderate temperatures, biodiversity and gravity our knees understand. The comparison becomes awkward for the galaxy. This does not reduce wonder, it sharpens it. If Earth is rare, then life here is more valuable, not less. If breathable worlds are difficult to assemble, then stewardship becomes less optional. If civilization arose atop a narrow chain of favourable circumstances, wasting it casually seems poorer judgment than ever. Sometimes astronomy's most practical lesson is conservation. You look outward and become more careful inward. There may one day be settlements on Mars, stations near Europa, floating platforms above Venus, or ships bound toward distant candidates like TRAPPIST-1A or Proxima Centauri b. Those futures may come, yet all of them would begin from here, from one planet whose air asks almost nothing in return except respect. We began with a simple thought that becomes larger the longer you hold it. Are there any other planets we can breathe on? At first, it sounds like a matter of yes or no. Somewhere out there, perhaps a world with oxygen, comfortable pressure, mild temperatures, oceans, clouds, and a sky that would not mind our lungs. Or perhaps not. But along the way, the question changed shape. It became about chemistry, about stars, about gravity, about time, about geology, about oceans hidden beneath ice, about planets too large, too small, too hot, too cold, too stormy, too thin-aired, too thick-aired, too close to their suns, too far from their suns, or simply too far from us. It became about how difficult it may be to create something we often treat as ordinary. Breathable air. That phrase is almost casual on Earth. We say it as though it were default setting. We open doors, walk outside, talk while moving, laugh in cold air, yawn on buses, sing badly in kitchens, run for trains, sigh at emails, fall asleep beside open windows. All of it depends on a planetary arrangement so intricate that the more we study the universe, the more remarkable it appears. A star stable enough, an orbit gentle enough, a world large enough to hold air, small enough to remain manageable, water in abundance, geology still active, climate feedbacks that did not fail, life that reshaped the atmosphere, time enough for complexity, luck enough to survive setbacks, and then, eventually, us. We looked at worlds close to home, Mars dry and thin-aired, still carrying the memory of rivers, Venus, brilliant in the sky and brutal beneath its clouds, Moon, silent and airless. Titan, cold and wrapped in orange haze. Europa and Enceladus, where oceans may move in darkness below ice. We looked farther outward too. Proxima Centauri b, nearby and uncertain. TRAPPIST-1e, one among a family of possibilities. LHS-114, OB and other candidates whose names feel technical now, but one day may feel famous. Some of them may host air, some may host oceans, some may host life, some may host nothing but wind and stone. For now, many remain hidden behind distance and the limits of our instruments. We know them first as data, then as models, then as stories we test carefully. Perhaps future generations will know them better. Perhaps one day a telescope will deliver a signal so persuasive that the world pauses together. A rocky planet, temperate orbit, stable star, atmosphere with oxygen, water vapour, methane in tension, clouds shifting with seasons, a spectrum that whispers not certainty but invitation. If that day comes, it will be historic. Yet there is another truth that deserves equal weight. Even if a breathable world exists elsewhere, tonight you're already standing on one. That fact can become strangely invisible through repetition. We adapt quickly to blessings. Air becomes background, trees become scenery, rain becomes inconvenience, soil becomes dirt, oceans become destinations rather than planetary miracles. We learn to ignore what works because it works so consistently. Then astronomy reminds us. Most places do not. Most worlds we know would crush, freeze, scorch, suffocate, irradiate, poison, or isolate us. Many offer beauty without mercy. Some offer chemistry without kindness. Others offer hidden possibilities beneath hostile surfaces. Earth offers something rarer. Ease, not perfect ease of course. Storms come, droughts come, fires, floods, earthquakes, disease, hardship and grief all belong to life here. This planet can be stern, but even in difficulty, it remains fundamentally supportive of our kind. The air is usable, water cycles, food grows, temperatures over large regions allow unprotected life. Ecosystems, though strained, still function. Dawn keeps arriving. That baseline generosity is easy to overlook until comparison appears. We also asked whether finding a breathable world would mean we could truly live there. And the answer, as so often, was complicated. Air helps. But home requires more. It requires memory, community, repair, trust, food, language, art, law, children, old stories, future plans, places to gather, places to grieve, places to laugh, places where nobody notices they are breathing because life is busy happening. Perhaps one day humanity will build that elsewhere. Cities under domes on Mars, stations drifting in the clouds of Venus, habitats carved into ice near European seas, generational ships crossing dark between stars, colonies on distant planets where the constellations are wrong and the children think Earth is the exotic old world. Such futures are possible enough to imagine seriously, but all of them, if they come, begin here. From forests and laboratories, from launch pads and classrooms, from engineers and farmers, from scientists reading faint spectra, from people caring enough to ask difficult questions, from one biosphere lending us the chance. There is comfort in that. We do not need to diminish Earth to dream beyond it. Curiosity and gratitude can share the same room quite peacefully. We can search the galaxy for other skies while caring more deeply for the one above us now. Those are not opposite instincts. They are companions. One asks, what else is there? The other asks, what is already here? If you're listening late at night, perhaps the room is quiet now. Perhaps the day has finally loosened its grip. Perhaps outside your window there is wind moving through leaves, distant traffic under clouds, rain on glass, insects in summer air, or winter stillness. Whatever surrounds you, it is part of an atmosphere generations before you inherited and generations after you may depend on. a thin layer of gases around a small rocky world circling an ordinary star. So ordinary that it became extraordinary. Somewhere under another sky, perhaps another being has wondered whether worlds like theirs exist. Perhaps they have looked at the stars and asked if breathable planets are rare. Perhaps they too have not yet realized how lucky they are. And here beneath our own sky, with lungs rising and falling almost unnoticed, we can rest inside the answer we already have. Thank you for spending this time with me. Sleep well, breathe easily, and if your thoughts wander upward for a little while longer, they will be in good company.